So hello everyone out there. So I'm Spyros Gidaris. I'm a research scientist at Valeo AI. And now in this CVPR with Karteek from INRIA Grenoble, Andrei from Valeo AI as well, and Relja, we're organizing a tutorial on annotation-efficient learning. This marks the beginning of this tutorial. So what I will explain you now what we will see. So I will give you an introduction and motivation for this tutorial. So we have seen that over the past few years, deep learning methods have achieved impressive results on a series of image understanding tasks, such as image classification, object detection, semantic segmentation, and so on. The typical way to train models in order to achieve good results, deep models in order to achieve results, is to first predefine a set of visual concepts, the concepts that you want to learn, then collect diverse large number of examples for each of them, and finally choose your favorite deep learning architecture and train on a cluster of GPUs for several days or even for several hours, even days. At the end, you will have a model that will probably achieve very good results on the test dataset. So all is good, right? Unfortunately not, because in real world, things are not so simple. First of all, the deep models need massive amounts of manually annotated datasets. Building such datasets requires to employ hundreds or even thousands of human annotators that will clean and annotate the raw visual data that you have. This is a very time-consuming and tedious process. Imagine, for example, that in order to annotate an image for the semantic segmentation task, as this image over here, where you have to annotate each pixel, it might take more than an hour. Also, because of this tediousness, it's prone to human mistakes in the annotation process. But there is worse than that. In some domains, such as medical imaging, it's really hard to obtain annotations, either because of privacy concerns or because of not knowing what exactly to annotate, what information to provide to your model. Also, new objects or different granularity of classes appear all the time, such as people on scooters or some new types of cars and so on. Ideally, you have to deal with them while making sure that you don't regress on the previously learned task that you have validated. Unfortunately, typical supervised methods do not work well in this scenario. Actually, to avoid forgetting the prior data, you have to train both on the new data and the initial data set, which is very annoying because it imposes expensive update cycles for the applications for which you need a deep model. And because maybe after you train the initial model, you don't have access to the initial data set, so it's not possible to do it anymore. Also, in real life, objects or situations that you encounter follow a long tail distribution. This means that some objects are very frequent, so in theory it's easy to collect thousands of examples for them in order to learn them, while some others are extremely rare. For example, Illipica here is a rare and endangered mammal, and only 1,000 of them have been left. Also, it's very few photographs of it exist, so it's very hard to learn with a deep model this class, this object. Also, the new Tesla car, for the new Tesla car, very few images of it exist in urban driving scenarios. So nevertheless, even for such rare objects, you want to be able to learn your model to work well with them. So you would need to quickly learn novel concepts using very few training examples. For humans, this is not a problem. For example, given this image of the new Tesla car, we are able, without any problem, to learn to recognize it from now on. In contrast, deep learning models struggle to do that. On the other hand, in many cases, acquiring raw label data is actually very easy. Imagine, for example, that hundreds of millions of images are uploaded daily on Facebook or other social media platforms, and similarly, hundreds of millions of videos. Ideally, we would like to exploit such raw data in order to learn better image understanding models. Unfortunately, if human supervision is prerequisite, it's impossible to do that. So typical supervised methods are unable to cope with such situations. In contrast, a child does not need millions of annotated examples in order to learn how an object looks like. Also, humans we learn throughout our lives while retaining knowledge from past experience. So there is obviously a gap with the ability of humans to learn. The next big challenge is in artificial intelligence is to close this gap and make deep learning work with limited annotated data, using in never-ending and continual learning settings. So the goal of this tutorial is to present methods in this regard. Specifically, we will cover three subjects. Karteek Alahari will cover the subject of incremental learning, where the goal is to learn models that are capable of continually adapting to new data without forgetting prior knowledge. Later, I will cover the subject of few-shot learning, where the goal is to learn models that are able to efficiently learn novel classes from very few training examples. And finally, Andrei and Relja will cover the subject of self-supervision, where the goal is to learn covenant-based representations without any human supervision. This is the program of the tutorial. In a few minutes, my part, the introduction, is finished. In a few minutes, Karteek will present the incremental learning subject. So stay tuned.
Good morning, everyone. Thank you again for joining us on this tutorial on annotation-efficient learning. So we'll just wait for a few minutes so we sync the time. And I'm going to start with my part on incremental learning at 8:45 Pacific time. Hello again to everyone. So just a quick note that we will be interacting with you through the chat that is available on YouTube. So if you have any questions during the course of this tutorial, please type them in through YouTube and one of us will pick them up and answer them as and when possible. So please don't forget, if you have any questions, don't hesitate, type them into the YouTube platform. Okay. And for those of you just joining us, we're going to start in 2 minutes to sync the time. So that's 8:45 Pacific time. All right, so we're almost ready to start. So just a quick note for those of you just joining us. If you have questions, please send them in through the YouTube platform, and we'll be able to pick those questions up and then answer them throughout the course of the tutorial as and when possible. Okay, so I think I'm going to start now. So thank you, Spyros, for the introduction. And I'm going to be talking about incremental learning in the context of annotation-efficient learning. I am Karteek Alahari, and I'm a researcher at INRIA in France. So before we start going into the details, what exactly do we mean by incremental learning? So this is a research topic that has been known under several names. Some of them are continual learning, lifelong learning, sequential learning, or also never-ending learning. So all these kind of represent the same core concept of incremental learning. But what exactly do we mean by this? So let's pick a very simple scenario of incremental learning. So me, growing up in India, I've had the fortune of encountering exotic animals on the streets. So here is a scene where you see lots of cows. So I've always known what exactly a cow is, and I've never been scared of it, having seen so many of them growing up back in India. But then as I grew up, I got more interested in seeing the rest of the world, and then I traveled. And in some places, such as the Pacific Northwest, we encounter these other animals which sort of look like cows, but have nothing to do with it, and have different properties. But still, I was able to adapt my understanding of these class of animals to these new exotic types. But then all through this time, I never forgot my apparently holy cows. So I learned new information, but I always kept in mind, what I've learned throughout the past. So taking this concept from, what we do as humans to the case of machines, what we would perhaps like to have as a property is have a machine learning system sort of be able to learn a particular task. It could be any task, for example, image segmentation, if you like. And then as we move along in time, we would like it to be the machine to adapt to solve additional new tasks, such as tasks 1 and 2, and then in the end, maybe go through a whole set of tasks 1, 2, 3, etc., and then to get to being a powerful machine which can perhaps have similar properties as what we have as humans. But in contrast, what typically happens in machine learning is, we have these 3 stages of training on a set of data, then validating on another set of data, and then finally testing it. So the main assumption that we tend to make in machine learning is, that all the samples come from the same distribution, which is very well, especially when, we're looking at sort of benchmarks or, with some slight abuse of language, call it academic data sets. So all in well, several machine learning frameworks work very well in this scenario. But how does this setup go towards real world systems? So here I would say is, given the progress that we have seen in the past few years, we are sort of doing reasonably well on some real world systems, but there is a lot more to be done, in particular when we want to go to setups of embodied learning. So, people have been talking about embodied AI, for example, and here is a case where the current state of the art is fairly lagging. So before we jump into the details, I wanted to just give a little overview of the different types of machine learning frameworks in the context of a standard supervised learning framework where you have training data on which we are able to learn our machine learning model. And this training data corresponds to a particular task. And for this particular task, we have data X and the labels that are associated with these data samples, which come from a data distribution, in this case, D1 for a task T1. And once we have learned a learner, we can then test it from data from the same distribution, but on data that we haven't seen during the training phase. So in this context, there are several machine learning frameworks that we've been seeing. So one of them is that of multitask learning, where we have several tasks going from T1 through TK, and for each of these tasks we have data distributions corresponding to them, and we sample our training data from these. And when all of these data are given to us, we can learn a machine learning model. And once we have it, we can test it on test data from all these test data distributions corresponding to these different tasks. So we are essentially solving several different tasks together. And then there is the case of transfer learning, where we learn a machine learning model on a source task given by TS, which means all the data comes from the corresponding source data distribution. And once we have this, we would like to transfer all the learned model information that we have to a target task given by TT and its corresponding data distribution. And we'd like to benefit from the additional data that we have also in our source. And this could be for cases where we have, for example, let's say very few data samples for a particular target task T, but we would still like to be able to perform well when there is test data from that corresponding task. And a variant of this transfer learning is that of domain adaptation, where we are interested in the same task T1, and we have data that corresponds to two different distributions of the same task. So you have a source distribution T, DS, and then a target distribution DT. And we would like to learn jointly on these two domains and be able to recognize test data that comes from my target distribution. So from this target domain, so to speak. And another more recent framework that we've been working on is that of meta learning, where we have a global distribution for all the tasks that we are interested in, and we'd like to split it into several individual tasks, and we sample data from these corresponding distributions of these different tasks that we have sampled. And from these, we learn what is being called as a meta learner. And once we have this meta learner, what we would like to do is sample a different task that we did not train on, and then test our learner on this particular data, right? So this comes with its own challenges. And then another framework in the context of supervised learning is that of online learning, where we have a single task T1 that we are interested in, and there is data that is sort of being given to us continuously. So at time instance T1, perhaps we have data samples from X1, Y1, and as we go along in time, we have a lot more data that comes to us. So, and what we would like to do is learn from all these samples and then still be able to test from data that is coming from the same data distribution. And a related task that we now are interested in is that of continual learning, where we not just have a single task, we could potentially have multiple tasks T1 to TK, and we have data corresponding to each of these tasks, which come at different points in time. And what we would like to do at the test stage is to be able to test on all the tasks that we have seen so far. For example, at the beginning of the learning scheme, we have data corresponding to only a single task. So we would like to effectively recognize all the samples coming from that particular test data. And at time instant TK, we'd like to recognize samples that are coming from any of the previous K tasks that we have seen so far. So in this particular part of the tutorial, what I'll be focusing mainly on is that of continual learning, where you have several tasks coming at different points in time, and we'd like to be able to have a machine learning system that can handle samples from any of these tasks that have been seen so far. So this is the incremental learning setup, so to speak, that we are interested in, where we have data coming in at different points in time for corresponding to different tasks. So in this context, we have several types of incremental learning systems possible. So one of them is task incremental learning, where we'd like to go from task 1 to task 2. For example, this could be going from, let's say, image classification to object detection to image segmentation, etc. Or another variant of incremental learning could be in terms of the classes. So we fix, let's say, a task, that of image classification, and then we would like to go from classifying samples of class A to class B to class C, and finally to be able to do it on all sets of classes that we're interested in the classification problem. And then a slight variant of this could be that of fixing a single task, and then changing the domain, perhaps going from images that we see in the natural world to images that deal with medical imaging, etc. So we would like to kind of have an incremental learner that goes or adapts from one domain to another and still recognize all the domains jointly towards the end of the training phase. So this whole idea of incremental learning is, it's not something that has just been invented. It is kind of a classical problem in machine learning and has existed in several different forms over the years. So, and people have also proposed various sorts of solutions to address this. One of them being, zero-shot or few-shot learning, where you could think of it as sort of the extreme case where you don't have training examples for some of the unseen classes, right? So Spyros will be talking a little bit about few-shot learning a bit later on. And another proposition that has come up is one where we, instead of updating, just our learning model incrementally, what we can potentially do is to continuously update a training set, which means we'd have an ever-growing training set. So we essentially keep all the data and we just simply retrain on all the data that we have collected so far. So this is, again, another possibility, and it comes with its own advantages and disadvantages. And a third potential thing that we can do is, we can say that, okay, we're not going to change the representation of our data. We will use the same representation that we have learned so far until, let's say, time instant t, and we'll fix this representation, and we'll just simply learn, in the case of classification, just a classifier by using this fixed representation. So we adapt to the new classes that we're seeing. So here we are obviously simplifying the learning problem by splitting the task of learning the representation and learning the classifier into two different sort of entities. But it again has the disadvantage that sort of goes against a lot of work that is happening in computer vision these days of what we would like to do is to learn a data representation that is ideal to the data that is available during the training phase.
Karteek?
Yes.
To interrupt you for a while, there was a question on the chat of if you could clarify meta-learning.
Right. So
just to mention that I will also explain meta-learning in my part.
Yes. So I think that's a perfect answer. So it in itself is a great topic that needs to be covered in detail. So I think Spyros will cover that a bit in his part, which is just after my talk. And if at that point it's still not clear, I'm sure we can ask the question again. Thank you, Spyros.
Yeah.
Okay, so now in this context, so just to set up the scene, what we have is this incremental learning setup where we could either have tasks or classes. So I'm going to be using them interchangeably. So we're going to be focusing just on, let's say, class incremental learning setup. So I could sometimes interchange the words class and task. So the other frameworks, we'll leave them to the side for the moment. Okay, so given this problem of incremental learning, what are the potential simple solutions that we can think of? So the first simple thing that we can do is just simply do a brute force solution. So where we don't want to do anything incremental. So here I'm going to take the deep learning network as the base, let's say, machine learning model that we're going to be looking at. So this is our original model, where in the test phase, we're going to take a test image and pass it through all our layers, and then we would like to classify it as belonging to, one of the tasks or classes that we have seen so far, identified by tasks 1 through n. Okay, so now in the brute force solution, what we can think of doing is just do a joint training mechanism where we would like to, consider data of all the classes together. So classes that here we have seen in the past, which I'm calling as old tasks, and we use the ground truth information there to kind of learn the parameters of the entire network. And then we have data corresponding to our new tasks, right? So we have ground truth available for both of these because we've just simply decided to train on all the data together. Okay, so this is what I'm going to be calling as sort of the golden baseline, because this is potentially, the best thing that we can do, train on all the data together, right? So just to kind of separate the feature extraction and the classification part. So here is the representation, of the layers of the network that do not correspond to the layers of the network except the last classification layer. So this is what is the current state of our model. And what we are now doing is adding components to the network, especially to the classification layer. So we are able to expand our network to the new set of classes, right? So this is the change that we would do when we are going from, a network that can handle only our old data, so the previous classes that we have seen, to a network that can handle the entire set of data, including old and new. Okay. So
Karteek?
Yes.
Sorry to interrupt you with another question. No. Was if the task consists of learning several novel classes by the classifier. This is an example.
Right. So there will be. So I'm not just talking about one class being added. So that could be one case, but you could also add several classes together. Is that the question? Do I understand correctly, Spyros? So can you add multiple classes at the same time? And
the context is not very clear from the question to me, but I think you meant that if a task consists of learning several novel classes by the classifier.
Yes. So we can have just one new class, or you can have several new classes added. And the task now is to, let's say in the case of image classification, to classify on all the set of classes you've seen so far. So which means the old set of classes shown here, and also the new classes that are added, which can be one or several. Okay. So in this case, when we train on the entire set of data, it is obviously computationally expensive, when you add hundreds and thousands of classes and millions of data samples in the training set. Another perhaps more critical thing that we should also think about is we may not have access to all of the old data for us to simply, retrain the entire model. And this could be for several reasons. One of them could be limitations of storage. We may not be able to store all the data. Another, a more serious concern could be that of privacy. We may not have access to all of the data because there is perhaps some potentially sensitive medical information, medical images, etc., which can potentially identify people, so they are not shareable to everyone. And also that this kind of method will go on until a while, but it would obviously not be very scalable. So these are the reasons why we would not want to just go for a simple brute force case. So one naive solution could be that of what I call as sort of the feature extraction method, where we treat the part of the network corresponding to the features, so all the layers except the last layer doing the classification, as fixed, so we don't fine-tune any of them, and we just simply learn the new layer or layers in some cases that we've added for the new task, which means we're only using information corresponding to the new set of classes, and all the rest of the network has been fixed. Okay, so here is what I mean in a slightly different way, where everything shown here in this in this shaded region is kind of fixed. So we're not learning any of these again. And what we are learning is only the new part of the layers that we have added corresponding to the new set of classes. Okay. So this kind of leads to suboptimal results because the feature extraction that you have learned is specific to the old classes that you have seen. So it hasn't been kind of adapted to the new classes that you're seeing. So this may be okay when there is a strong correlation between the old and the new classes. But imagine all the old classes have been learned on classes such as buildings and road scenes, and suddenly you want to add sort of objects corresponding to indoor scenes such as tables and chairs, and there is very little overlap between these set of classes. So this would not be an optimal thing to do. So another nice solution here is, instead of fixing all the layers, what we're going to do is, do you know what we classically do in several other contexts that are fine-tuned? So we're going to change the parameters of the previous layers. So either some of the layers or all the layers, depending on the choice that we would like to make. And we're going to use only the new data to essentially retrain and adapt the parameters of all of the layers or the selected layers in our network. Okay, including the new part that we have added corresponding to the new classes. Okay, so the only part that is kind of remaining fixed is that of the classification layer corresponding to the old data, because we don't have any of this old data, and the rest of the network is being adapted to new data, right? So this leads to a phenomenon which I'm going to define in just a little bit, which is called as catastrophic forgetting, where we are going to do very well on the new classes, but we're going to forget a lot of information about the old classes. So I'm going to take an example of, in this case, a computer vision problem of object detection, and we'll investigate what exactly happens in this case of catastrophic forgetting. So here is our favorite CNN that has been learned for detecting object. Initially, let's say it's been learned for 3 classes, including person, object detector. Now, what we would like to do is extend this initial network that we have by adding a new class. So in this case, I'm taking an example of adding one single class of horse, which means I now have training images for learning the category horse, right? So which means now the final layer of my network can predict 4 values corresponding to 3 of my old classes, which include person, and my new class horse, which is the 4th class I've just added. Okay. Now the question is, how well can we perform on detecting horse, which is my new class, and also my old classes, including person, right? So all the 4 classes essentially. So just for illustration purposes, I'm going to call the first network, which is my network consisting of old classes, as A, and the new network that I have as B. Okay. So let's see how well this network, B, that has been adapted to the new class works. So as a comparison, let me put a method, the golden baseline, where I've trained on all the 20 classes. So here is a network that was trained on the standard ImageNet 20 classes, so which include person, horse, and several other classes. So this is the overall result that we have on the entire set of 20 classes. Okay, the accuracy for detecting these objects. And here I've simply just averaged the accuracy for the first 10 classes, right, which correspond to my initial set of classes. So my initial network A has been trained on classes labeled from 1 to 10. And it has not seen any of the other classes, 11 through 20, which means I cannot compute the performance on the new remaining 10 classes. So we just have this. And now I have my B network, where I'm adding these remaining 10 classes, right? My new set of classes. And here is a point where typically in a talk where I interact with people directly, I would say, what is the performance that you would expect for this case. But given that we cannot do that, so I'm just going to show here to see that, to show you that here, the performance is dramatically lower on my old set of classes, because I don't have any of the data that I've, for the first set of 10 classes. I'm not using it when I'm relearning the network for the new set of classes from 11 through 20. So as expected, the performance would go down, but here there is a dramatic drop in performance from just over 68 to just about 13. Okay, but as you can see, the performance on the new classes 11 through 20 is reasonably is reasonably good, because we have data corresponding to these classes, and the model has learned well to kind of detect these objects. But as you can see, there is a difference. There's still a difference between what you would expect when learning on the entire set of classes. This is mainly because you have a lot less data when you're kind of retraining the network, and the data has been seen in 2 different ways. So, and then I should also say that here we're not looking at an explicit background class, which also kind of adds to some of this decrease in performance. So here again, I'm showing the one of the most extreme cases of this catastrophic forgetting. Depending on the choice that we made of fine-tuning, let's say in this case, all the layers of the network. So if you change and fine-tune fewer layers of your network, you would see an improvement in this performance, but it would still be far away from the original 68. So but because of the drop in performance on my old classes, the overall performance obviously is significantly lower than what we would expect. So this is not, it should not come as a surprise, because what is happening here is that there has been no guidance in sort of retaining the information that we have for our old classes, right? So this phenomenon has been identified, pointed out several years ago, and has been called as catastrophic forgetting, because there is a catastrophic drop in performance, right? And there have been in it some methods that have been proposed for networks from the 80s and 90s, but they don't really adapt well to the current models that we use, which are significantly larger than what we used to use in the past. Okay, so let me kind of set up this problem of incremental learning and what I'd call as, let's say, the rules, because there's several variants that people have been looking at in the context of incremental learning. So we're going to look at one particular setup in this tutorial. So here we have tasks that are given to us. I'm using the example of having tasks one at a time, but like I said, you could have several tasks, coming at different points in time. Okay, so what we want to do is learn one task after another, or learn many tasks after another. What we would like to do is do this or achieve this incremental learning framework by not having to store all the data from my previous tasks. Okay, so we don't want to store any of the data. So the other thing that we would like to achieve is to not increase the memory footprint, so it grows uncontrollably over time. So it would grow in some way, so we would want to make a trade-off, but not have the memory footprint kind of explode, right? So, and then we would also like to achieve this this goal of incremental learning without forgetting any of our old tasks. So these are kind of, let's say, the ideal setup or the ideal rules that we would like to do. But then given to have a more realistic setting, we kind of will make some adjustments. So instead of having this requirement of not storing any data from previous tasks, we can make some adjustment and maybe store some data from the previous tasks. Okay. The other thing I said about memory is, we don't want the memory footprint to grow uncontrollably. So we would allow it to grow a bit, but we don't want to allow it, for it to grow significantly. And the other thing that we would like to achieve is, allow a little bit of forgetting, that is, forgetting in as we are learning these new tasks, but not completely forget them. Okay, so this is the sort of the setup that we're going to be looking at. So maybe at this point, I don't know, Spyros, are there any other questions?
So far, no, but I guess, I don't know, would you like to make a stop for questions? Or
No, I think it's okay. I think I'll continue. And then if there are questions that come up, then yeah, please let me know.
Okay.
Okay. So what are we going to do in the sort of roughly just under 1 hour that we have for this part of the tutorial is we're going to look at sort of several different flavors of approaches, going from, what I've grouped them as sort of regularization-based approaches to rehearsal or replay-based approaches, and to some, or just one example in this case, to architecture-based. So there are other possibilities also of handling sort of incremental learning problems, but in the interest of time, I'm going to give a few examples of each of these different flavors, so to speak. And then, there's several other approaches that are out there. And hopefully towards the end of this talk, I'll be able to give some pointers to, where we can find other information. And later on, if there is time, then, I'm going to be looking at, the image classification problem as sort of the running example for the majority of this talk. But if there is time, then maybe I'll take, the problem of object detection and see how we should adapt some of these methods for the case of object detection as well. And then I'll conclude with sort of some takeaways on this topic of incremental learning. So I'll jump right in. Yeah. To
make a question from the chat is if during training we would know that there is a new task coming, or the algorithm will have to detect it by itself.
Right. So that's a very good point. So we'll come to it. So there are some methods, or I would say majority of the methods, that kind of expect the entire set of tasks, but they'll just come at different points in time. So that is kind of the assumption that we're making. We know the entire set of possible tasks. So, right. So, but there is some recent work which kind of looks at sort of task agnostic approach, which I'll give a pointer to that towards the end. But we don't know what task is coming, but we do know, let's say, the total set of possible tasks that we have. Okay, so that's the evaluation setup that we're going to be looking at. Okay, so regularization-based approaches would be the first thing that we look at. So here, like I said before, one of the reasons for this dramatic drop of performance of also known as catastrophic forgetting is that there is no sort of information sharing from the previous classes or tasks that we have. So the point of regularization methods is to kind of address this, where when you're training for a new task or a set of new tasks, what we would do is add a regularization term to the loss. So essentially modify the loss. In some ways, kind of add a term that will penalize this behavior of catastrophic forgetting. So we'll see how this can be done. And there are two ways that people have been handling this. One is that of focusing on the data. And the other possibility is sort of focus on the model or the prior. Okay, so we'll start with the first one of focusing on the data. So this is based on previous work from Jeff Hinton and his colleagues. I think the reference is slightly later on in the slides, of knowledge distillation, where what we would like to do is kind of preserve the responses that we have. So as soon as we have a new task, what we're going to do is add the part of the layer that corresponds to these new tasks. But instead of just using the annotations for the new task, what we're going to do is also kind of use a copy of the model that we have had so far and compare the responses of the previous model, which can give us responses for all of the old tasks, and then compare them to the responses that the new model is giving. So we're going to fine-tune the parameters of the entire network, but while doing this fine-tuning, we're going to add a cost function which kind of measures the difference in the values that corresponds to the new part, of the old part of the network, and then the previous model that we have stored. So this will, maybe I'm going to go through a little bit quick this part, but it'll come back slightly later on when we go through knowledge distillation. So then it'll be a bit clearer perhaps. So what this previous model's output for old task allows us to do is to kind of make sure that the parameters that we are learning don't go too far away from the parameters that we have had for the previous old task. So we're essentially making sort of, think of it as an L2 distance between the outputs that you're producing for the part of the network that corresponds to the old task, and then to the copy of the network that you've had. So in this case, what we are doing is we have two copies of the model. So the model that we're going to update all the time, and the old model that we have, which we're not going to change. So the old model is going to give us responses for all of my previous tasks or previous classes. And I'm going to use these responses and then compute a difference between what the old model gives versus what the new model is doing, right? So it's a sort of a simple regularization to make sure that the model doesn't go far away from what it was in the past. And the second part of this model is fairly standard. Think of it as a sort of a cross entropy loss, where you have annotations for your new data, and you can compute the predictions of this new network, and compute the loss given the ground truth for these new tasks. Okay, so this obviously is a very simple method, but it works pretty well in practice, because especially when the new tasks that we have are very related to the previous tasks that we have seen. But what has been seen empirically is that if the two tasks are unrelated, then the results would be not what we expect. So here, that would be the sort of the disadvantage of not performing well when the tasks are very unrelated. And here is the case of memory. I put a question mark because in some ways it can be seen as a disadvantage, in that we need to store an entire copy of my old model, right? Which means parameters that correspond to all my feature extraction layers and then also my classification layer, which means you're essentially doubling the memory footprint, which may be fine depending on the size of the network that we have. But in some cases, if the network is huge and there are severe constraints on the memory capacity, we may not be able to store the entire model, right? So then there is a case of other model-focused approaches, where instead of focusing on, sorry, I'm going to go back to the slide, on the outputs, so which means on the data that we have and what the data generates as outputs of my network, right? So this could be seen, the logits, for example, that you have in the network, or for example, even the responses from the last but one layer of your network. So in contrast to that, what we're going to do is add a regularization term on the parameters of the model itself. So here is a loss function that focuses on introducing a model-based regularization, where you have the loss function, which corresponds to two parts. The first part is the standard loss on the new task that you're adding. So this is the B in the example that we have seen in the case of the computer vision task that I showed you earlier of object detection. So that is, for example, can be a standard cross entropy loss, and theta n corresponds to the new set of parameters that you're learning once you've added n tasks to your problem. Okay, and the second part essentially corresponds to the regularization, but which is now defined on the parameters itself. So here, theta n k corresponds to the kth parameter from the current state of my network, and theta n minus 1 corresponds to parameters that you have seen so far when you have learned the model on n minus 1 tasks. Okay, so here is a simple L2 difference of of these two parameters that you have. And there are several ways of kind of weighting this, this loss function. And what is typically done is to kind of penalize changes to important parameters. Okay, so we'll define what we mean by important. And there are different possibilities of kind of, computing this importance. So what we are saying here is we would like to have a very high penalty if we find that a certain parameter in my model is very important to keep the performance on my old as well as new tasks. So we would give it a very high lambda, for example. And if we find that there is a parameter amongst my millions of parameters in my network, which is not very critical for, for any changes to the model, what we're going to do is say that, okay, we will have a very low penalty for that, and we'll allow this this parameter to be changed. Okay, so let's see a couple of examples of what are the possibilities for this importance computation. Okay, so the first example is that of elastic weight consolidation, a paper from a few years ago, where what was proposed is that we're going to have an individual penalty for each of my previous tasks. So in contrast to what we had here, I just said, okay, we're going to look at the current set of parameters and just the previous set of parameters that we had. Whereas in this particular case, this work looked at storing all the previous sets of parameters that we've had. So here you have, let's say, n-1 tasks. So for all the n-1 initial tasks that you have, we're going to compute a regularization term based on that and then sum it up for computing the regularization for my current nth task. Okay, and then the choice of the lambda in this particular case was based on computing Fisher information. So just computing on the data to see how important is, is a certain set of parameter for making my final decision. Okay, so you can think of it as sort of entropy. It is related to that as well. And I'm not going to go into the details of this because in the interest of time, but this is one example where you have computed this importance weight based on Fisher information. And you've, in addition to storing just the previous set of parameters, we've stored all the previous parameters that we have learned so far. So as you can imagine already, that the memory footprint for this is going to be significant because we're storing a weight for all the parameters in my network for all the previous tasks that we have. So just to understand, I think what's important maybe is to understand sort of at the intuitive level, what are we trying to do, by kind of adjusting these thetas, the old and the new. So for that, I've picked this graphic, a very simplified view of what is happening. So just taking an example of two tasks, and imagine there are only two parameters denoted by θ1 and θ2. And what I'm showing here is sort of the space of my parameters. And yes, Spyros?
So there is a question in the chat. So how do you determine which parameters are important? Is lambda of k learned or hard-coded?
So, sorry, the k is over all the parameters, right? So that is the generic case, but given the size of the network, you can choose to have maybe only some of the parameters, but that again is a choice that is to be made. But for the general framework that was proposed here, this is on all the parameters of the network. There is no choice. And what determines how important a parameter is the lambda value that is computed for that particular parameter. Okay.
And there was another question. It was a bit earlier. You mentioned somewhere embodied learning.
Right. So that, I'm not going to go into the context of this tutorial, but I can point out, actually, there was a wonderful tutorial, I forget which day, or a workshop maybe even, on embodied AI. So I would recommend, the readers or the viewers to see that. But it's just, I use it as an example to show that embodied AI is one, where you want to have agents in a real world environment, interacting with different objects and other agents and other people. So that kind of increases the complexity of the learning problem. And incremental learning is something that would help in these kind of contexts, and something that is maybe not we have completely achieved at this stage. So I'll just leave that there, and maybe recommend the viewers to see that if they're interested. Embodied AI, I think it was on Sunday or Monday, I can't quite remember, unfortunately. Okay, so here is a space of my of my loss function, so to speak, in this parameter space. For the case when you have just a single task one, okay, so blue here indicates low value of the loss function, which means we would start at some initialization of my parameters theta and theta1 and theta2, and then do a gradient descent, and hopefully end up in this ideal low blue region. Okay, so now what happens is, once we add task 2 into the space, so here the yellow dot indicates the initial optimal value for my parameters, but this optimal value is no longer optimal for my task 2. And if we did not consider any of these regularization terms, what would happen is, if you do gradient descent in this by using all data corresponding to task 2, we would go to the best scenario in this space for task 2, shown in this dark blue region. But if you were to see how that corresponds to for task 1, it is obviously not an ideal setup. So by using this Fisher information, what we would like to do is, instead of choosing this particular direction for all the gradient steps, we would like to move into this space where it is ideal both for task 1 and also for task 2, right? So this is what we are trying to do. So another kind of way to understand this is this nice figure from the paper. So imagine you have, again, two tasks, task A and task B, and all this region here in gray corresponds to region in the parameter space where there is a low error for task A. And now, as soon as we introduce task B into the picture, and if we do not have any penalty with this regularization term, what would happen? We would suddenly go to the optimal value for only this task B. But instead of that, what we would like to do is push the parameters into a space which is ideal for both task A and task B. Okay, and if you were to just simply have an L2 difference of parameters theta A and theta B, you would get to something that is not optimal, right? By introducing these individual penalty weights for importance of parameters, because there are way too many parameters and we cannot adapt to all the parameters, and just simply looking at an L2 difference does not do the job. And if we give importance to different parameters, we would go to a common good region. Okay, so what is the advantage of this method? It is that it is completely agnostic to the architecture. We're not looking at what exactly is the architecture in this context, and it has been shown that it gives pretty good results, empirically speaking. But the sort of disadvantage of this method is that sort of by looking at these parameters in sort of a very local way, and you're making these local gradient descent updates, and you're only looking at a subset of the parameters at every time instance. There's no sort of global set of parameters that are being optimized all together. So you are adding them up, but still adding them up individually. So there is some trade-off you're doing by looking at them sort of only locally. So that is sort of one of the disadvantages of this method. And another point which can be an inconvenience is that you need to store importance weights, which means that you're essentially increasing the memory footprint by the size of the parameters. So if you choose all the parameters in this summation k, then it would rapidly explode. But if you choose a subset of them, you would keep it in control. But again, there is an interesting question there is, if you want to only choose a subset of parameters and then give importance weights only to those, how would you go about choosing it? Okay, so a variant, of this particular model-focused regularization methods is that of memory-aware synapses from just under a couple of years ago, where instead of considering all the previous tasks, we're only going to consider just one of the latest previous task, theta n-1, and its parameters theta k, and then we're going to compute this lambda in a different way. What we're going to do is use the gradients to compute this, so essentially doing it from on the data side. So I'll give an intuition for what is being done here is, so this is the sort of the x-axis here denotes the training samples. Again, I'm showing a very simplistic view in a two-dimensional space, but the data is obviously in a very high-dimensional space. And what we have are the labels. In the case of classification, you have the object class labels for each of the samples that I have in my training set. And what we do is learn a function f, so essentially fit a curve to all my training samples by measuring the error between the prediction that you have on the curve here and the ground truth label. Okay, and what happens in the case of incremental learning is now you have data corresponding to other classes, right? So essentially we want to extend this initial function f that we have learned here in black to these new classes by kind of extending it to also these new classes. So we will compute the loss with respect to the ground truth on all of these new tasks. But in addition to that, what we're going to do is also look at slight perturbations of the data. So essentially giving us more training samples, whereas we had a very small set of training samples here. So what we're going to do is just slightly perturb the data that we had shown here in, if you can see the colors, sorry, in yellow, and sort of take a sample which is very close to it. And then we're going to use these new samples, which correspond to my old training data, and add them up into my regularization. So I'm going to compute the regularization with respect to gradients that are computed on all these data samples. So essentially it gives a little bit more support to the initial function f that was learned, so that it doesn't completely move away from this function. Okay, so again, I understand that I'm not going to all the details, but what is important to remember here is just that there are importance weights that we are assigning to the parameters, all the parameters in my network, and there are different ways of computing these these importance weights. One using Fisher information, the other is using the gradient information. So you take the gradient at different training points, okay, and use that to essentially compute these these importance weights. Okay, so similar to the elastic weight consolidation method, this method is also sort of agnostic to the architecture of the model that you have chosen. And in contrast to the other method, this leverages more the data and the output, in contrast to the other method. So again, this still has the same disadvantage that elastic weight consolidation has, in that you're kind of looking at this information only very locally. Okay, and again, depending on the number of weights, number of parameters you decide to consider for this regularization, which is typically all, but you can choose to have only a subset of them, you will have a pretty strong memory footprint. But given that you're doing it only for one of the latest previous tasks, it is significantly lower than the previous method. So just to sum up this part of regularization method. So we saw just two examples very briefly, I should add. And there are several other alternatives, that are possible. One of them is that of path integral, or also known as synaptic intelligence, where we kind of observe, if for a parameter there are going to be large changes during the training, then we kind of compute an importance weight based on those changes. And there are other ways of computing these importance weights, or even more generally, just the regularization term itself. Okay. Right. Before I move on to the next flavor of approaches, Spyros, are there any questions on YouTube?
No new question, so you can continue.
Okay, thanks. Right. So the next class of methods is that of rehearsal or replay. Right. So here, so we're going to go deviate from one of the ideal rules that we set up for our incremental learning framework that we are considering here, and that instead of saying that we don't want to have any of my old data, I'm going to say that I'm going to store a few examples, right, from the previous tasks that I have seen. An alternative to that is also, instead of storing some of these samples, we could have, for example, a generative model which kind of produces data from these previous tasks, right? But in this context, there's several important questions that we need to consider. In that, how many of these samples, do we need to choose? How do we select these samples? And then how do we also use these models once we have chosen them from my previous tasks, right? So depending on this, on the answers to these questions, we have a wide variety of methods that are out there for this class of approaches. So I'm going to take two examples in this context. One of them is that of ICAL, which is a method that was proposed for incremental classification and representation. Okay, so in this particular method, so it goes more in the way of choosing a few samples, that are sort of representative, so to speak, which are closest to the mean of each class. So I'll go through it in a bit of detail, this particular method. And then we're going to use the idea that we saw before of knowledge distillation to kind of also adapt the loss function. So just to sum up, in one single phrase, so it is a clever use of, the available memory that we have. Right. So we'll go through this method in a little bit of detail. So overall, what this approach does is kind of splits the problem of classification into two phases. One, that of learning the features, and then once we have learned the features, it then uses a nearest class mean classifier to just simply classify the samples in the test phase. So let's see the training phase first, and then we'll go through the test phase. So what we have is a set of training examples for my new classes. So you have new classes represented by S through T, and there is data corresponding to all these new classes, and then they have their corresponding labels as well, ground truth labels, I mean. And we also have sort of a current set of model parameters that have been given to us based on a model that has been learned from 1 through S-1 of my previous tasks. Now, for all of these previous tasks, I also have a set of examples, which the paper in this case calls as exemplars, that have been chosen, right? So set cal p is the set of all of these examples chosen for all of my previous tasks. So each of these p represents a set of samples that are chosen. Now, assuming that all of these are given, the first thing that the training algorithm does here is to kind of update the representation based on all my new data, okay, and the exemplars that I have for my previous tasks, and the current set of parameters that I have. Okay, so that's just a simple update of the parameters, which I'm going to explain in a couple of slides. And then once you have updated the parameters, there are a few sort of bookkeeping operations that we need to do, which are not so important. There is a fixed set of memory that is associated with all the data that we can store from my previous tasks. So you can say either that I want to have 2,000 samples from all of my previous tasks. So which means that as you're adding more and more tasks, the number of samples per class that you can store will decrease, right? So this is the budget, so to speak, of your memory for all my stored exemplars, right? Which reduces as and when you add new classes. So that's the two steps here, which I've kind of ignored for the moment, where you first need to reduce the exemplar set of the current previous tasks, and then you need to find the exemplars for the new tasks that you're adding, okay? And once you have done those two steps, we have a new set of exemplars that now include all my previous tasks or classes through S-1, and then they go all the way up to T, including my current new tasks in a more general case. Okay, so now once we have, let's say, considered this this training procedure as sort of a black box, the next step that we would want to do is to classify. And here comes the next step of classification using this nearest mean classifier, where you have, let's say, an image that is to be classified. And for this image, we compute the feature representation, based on the features that we have learned during the training phase. And once we have that, we can compute the mean of all of the exemplars for each of my classes. So here I'm computing the means mu for all of my classes that the model has been trained on, right? So you have T classes that the model has been trained on, compute each of their means separately, and then we assign the label to this particular image based on what is the closest mean amongst all the set of means that you've computed using these exemplars. Okay, so that's the last step for classification. So what this approach has done neatly is to kind of separate the classification part by using this particular nearest class mean classifier, and then the representation learning. So let's just maybe go quickly into the representation learning, how exactly this happens. So here we have, our set of new training examples, okay, from these classes, and we have exemplars corresponding to all of my previous classes. So now using these two, I can combine them to make the entire set of training data, which has all the examples from my new classes, and then the exemplars I have chosen from my previous tasks. So this is now the entire training set that we have. So on this training set, we're going to compute essentially two losses. So the first loss is our standard cross entropy classification loss, which is computed only on the new classes S through T, which means you're computing or comparing the ground truth that you have, which is yi for a sample I, okay, and then the prediction of this particular instantiation of my network. So that's the standard loss, but that is only computed on my new samples. And then we have the distillation loss, which essentially computes the difference between what is the previous output that you had, which is stored here for all of my previous tasks, and what is the new output that this new network has been is giving us once we have updated the parameters. So the loss function essentially is using ideas from the regularization methods that we talked about, where you're updating the loss function with this new distillation loss, which is essentially computing the difference between the new predictions or the new let's say, if you like, the logit values that you've computed and the previous values that you were getting for this exemplar set. So we don't do it on all of the data, just the data that we have chosen to store. Okay, so what this method does, like I said, is a sort of clever use of available memory. So you have a budget for your memory and you kind of adjust it according to the number of tasks or classes that you have. Okay, so the downsides to this method are that of potential issues of storing the data. There could be cases where you don't have access to any of the old data for, let's say, privacy issues or other reasons. And the other thing that has been seen empirically is that ideally, these methods would like to have as big memory capacities as possible, right? So the more examples that you're storing in your exemplar set, the better it is. So there is a trade-off between how much you would like to store and how well does the network not forget the previous classes. Okay, just checking time. Okay, so now I'll take another class of methods and take one example from this class, which is that of a deep generative replay. So like I said, instead of storing the previous examples, I can also decide to kind of generate these examples on the fly. So this is a paper from a few years ago, where the model, which was called as Scholar, is essentially composed of a generator and a solver or a classifier, if you like. Okay, so that is the core component of this model. And what this method does is to kind of update both these components in every incremental step. Okay, so we'll see how this is done. So the overall training procedure is that when you have, let's say, one task, you learn the corresponding scholar for that task, which means you learn the generator as well as the classifier. And as soon as you get, a task T, let's say, what we do is we train this scholar T using data that is given to us for that particular task T, and the data that was generated by the previously trained scholar at task T-1. Okay, so which means we use, instead of storing the samples, all we have is a generator model, generator T-1, if you like, which is in the scholar. And we're going to use this generator to generate samples that correspond to all of my previous T-1 tasks and combine it with data from my, from my current task T, and then essentially relearn or update the scholar, which means the generator and the classifier. Okay, so let's see what happens in these two training procedures for the generator and the solver. So in the case of the generator, so this is our current task, which means we have the input data corresponding to that particular new task X, and then we also have the target labels, which are not used in the case of learning the generator. Now, we also have our old scholar, which has been learned on all of my previous T-1 tasks, and we use the generator component of this scholar to generate samples that correspond to my previous classes. Okay, now using these two sets of data corresponding to my current and my previous task, we now learn a new generator model for my new scholar. Okay, so here again, I'm not going into the details of what is the generator model, but for at this particular stage, that is not important. So there was a choice made for the generator in this particular work, but you can imagine, using your favorite generator model here. Okay, now once we have learned the generator model in my new scholar, we're now going to go about learning the solver. Okay, so in this case, again, we're going to use data from my current task T, which means we're going to use data, the input X as well as the target labels Y, which means we're going to use the ground truth labels that are given to us. Now, as previously, we're going to generate data from all of my previous tasks, t-1, and then because we don't have this data stored, we don't know what the ground truth labels are, we're going to rely on my solver to give me sort of pseudo ground truth labels denoted by y prime here, and then combine them with the training data that we have, sorry, the generated data that we have x prime, and use it together with data for the new task. So essentially, we are not only generating the samples x prime, but we are also generating the sort of the ground truth labels for all of these samples, and then use both of them together to then learn my solver. Again, the solver itself can be, your favorite solver, but a particular choice was made in this particular work. Okay, so the big advantage, of this method is that you kind of avoiding memory issues. So we do have a little bit of footprint for kind of storing the parameters of my generative model, but it is significantly lower compared to having to store all the parameters of my huge deep learning network, or storing all of my samples from my previous data, or or kind of having to manipulate a budget and reducing the number of samples as you're adding more and more tasks for storing the exemplars. Excuse me. Right, but on the downside, there is issue in terms of kind of accumulation of errors, because as you go from task 1 through 2 to 3, etc., you're kind of accumulating the errors that the generative model is potentially making. Both that, and also that the labels that you're predicting with your solver for the generated samples could also have errors in them, right? So there could be an accumulation of errors depending on how well the generator and the solver have been learned. And another potential issue is that of if the generator model, as was done in this case, is agnostic to the class, we may not have necessarily a good control on the types of examples that are generated. So you could have a bias in terms of maybe too many examples from task 1, but very few examples from task 2, and so on. So there could be some potential imbalance in this case. But again, this is something that can be overcome by kind of balancing, the data set that you have composed of the real current task data, as well as the generated data from all of my previous tasks. Okay, so that kind of is another example of the rehearsal or replay flavor of methods, so to speak. And now I'll just give one example from sort of an architecture-based method, just to give you a sort of wide spectrum of methods that are possible. So, right, so here is a work from a couple of years ago, where, here is a very, again, a simple visualization of, let's say, the filter or the parameters that have been learned for one particular layer of, of the model that you've chosen to perform your classification task on, right? So initially, when the model has been trained only for task 1, we learn the parameter values for all of these, let's say all of these weights in my filter, okay, which corresponds to one of my layers in the architecture, and we would do that for all of them. Now, what is done before we move on sort of to the incremental learning phase is we decide to prune, let's say 60% of my parameters that have been learned, right? So which means I'm going to set these parameters to values to 0, and then use only the other learned parameters for this particular task. So in some sense, what is being done here is that we are sort of making space for the future tasks, that we are likely to see. Now, which means that once we have fixed some of the parameters and say that these correspond to task 1, we are only now going to learn the parameter values for the rest of them, right? The ones that we have set to 0 for a new task that comes, so task 2 in this case. And then once we have done that, completed the training phase for task 2, we then make another choice of pruning another set of parameters from these new ones that we learned, right? So only from the task 2, we're going to make a choice and say, okay, I'm going to prune some more of these parameters and then make space for my new task, task 3, right? So here we have 3 tasks which have all been learned, and now we sort of have parts of my network which kind of specialize in learning different tasks. Okay, so it's a clever idea to kind of make space for, you know, other tasks that you're going to see. So the big advantage is that, you know, your memory consumption is fixed because you have the network fixed all the way from the word go, and you just keep adding the tasks. But now here, this links to one of the questions that was asked earlier on, like, do we know about all the tasks that are there? So we don't know what task is going to come up, but we do know sort of what is the total number of tasks. So we can sort of roughly adjust the parameters to, you know, and share them across all of the tasks. So, and empirically, it has been found that this method also, you know, works pretty well, actually very well in practice in some cases.
And I interrupt you with some questions from the chat. I will take them in inverse order. Okay. So the latest was if this method can be thought of as adding parameters for new tasks.
About this method on PACnet?
Yes.
So in this, right, so I guess one variant you could think of is kind of adapting the network by adding more parameters. So that leads to other methods in this class of architecture-based methods where we are saying that, okay, we're also going to adapt the architecture of my network by adding more parameters. But in this example that I covered, I said we have a fixed number of parameters and we just, you know, kind of make space for all the tasks. But there are methods out there which also kind of add parameters to the network, yes.
There are 2 questions about the generators approach.
Okay.
The first is if the quality of the generator and of the resulting solvers is degrading over time. And maybe this is also already answered, actually. But
yes, so that is sort of the accumulation of errors that can happen, you know, depending on how the generator is learned. So in a general case, yes, it can happen, but there are ways to handle it by, you know, adding additional constraints to make sure that the generator is making, you know, the errors it is making are not increasing over time. Yes, but in general, it can happen, but you need to handle that.
Mm-hmm. And another question about the generators is that why not using conditional generators to avoid using solver for generating?
Sure, absolutely. That is definitely another variant possible. Yes, absolutely. Okay, right. So I do see that. So am I right in saying I have just under 15 minutes, right, before I move on? Okay.
Maybe I will ask the remaining questions at the end of the presentation, just maybe.
Yes. So I'll give a little time. Yeah. Okay. Right. So given that we have seen, you know, these different flavors of incremental learning methods, clearly it is not an exhaustive list of all the methods out there, but just I picked a few methods, you know, to kind of show the variety of methods that are possible. So here I'll just briefly present a comparative analysis that was done in a recent work. And this was tested on 2 kind of data sets. One is a tiny image data set, and another one is iNaturalist. So you can find all the details in this paper that is referenced here. So this was done on these 2 data sets just so that you have a different order of scale, going from, you know, let's say 8,000 odd samples in this tiny ImageNet case for training to about over 60,000 samples in the case of, you know, the iNaturalist data set. Right. So and this work also used kind of a fair way of setting the hyperparameters, which is an important question in this context of incremental learning, because you don't have all the data for all the tasks to set the best set of hyperparameters. So there are trade-offs that have to be made, and you'll find all the details in this work here. Okay, so I won't go through all of the methods. So here is just a comparison of the regularization and architecture-based methods. So some of them that we have seen, like elastic weight consolidation, memory-aware synapses, PACnet, and what we are showing here is the performance on all the tasks. So you have 10 tasks in this tiny ImageNet case, and you add one task at a time, which means one class at a time. And what we see in each of these columns here is how the performance changes for a particular task as you keep adding new tasks. So which means task 1, given that it's the first task, you will see 10 points in this graph because you add 1, then 2, and then go all the way till 10. And the extreme case is task 10, which only has a single dot because it has only been trained once for this. The model has only been trained once for this particular task. So ideally, what we would like to see is not too much change, so pretty much like a flat curve for all of the previous tasks, and then the values to be as high as possible. Okay, and here in this little X, if you can see, we have what the performance of the golden baseline, where we train on all of the classes together. What is the performance for task T1 when you train on all of them together? So as you can see, there is still a big gap between any of the incremental learning methods and sort of the golden baseline. But what is interesting is that if you were to just fine tune, the performance dramatically drops, which is the case of catastrophic forgetting that I showed you. And whereas if you follow methods such as PACnet with the architecture-based approach, or memory-aware synapses, and a few other methods that we didn't cover in this talk, the performance degradation is acceptable. Okay, and you can see similar observations for all the other classes as well. Okay, so then there's a few more methods that have been compared here, which I'm going to skip now in the interest of time. So just as a general trend, what we observe here is that in general, the rehearsal or replay-based method, which stores some of the previous examples, they kind of only pay off when there are, when we're able to store a significant amount of previous data. Okay. PACnet seems to come up as one of the best approaches in this particular evaluation. And in comparing the two kind of importance weight-based approaches, the one based on memory-aware synapses, where you're only storing parameters from just the previous task, is the one that kind of is more robust to errors compared to the other variant. Okay. Now, here's a question. So now, given all these models, what should be the one that you should use? So just a few rules of thumb, so to speak, is that larger models obviously have more capacity to kind of add more and more tasks, but they also have the downside of overfitting to our previous classes. Okay, and another observation is that in terms of the network, the wider the network, it is better than the deeper the network. But again, this is an empirical observation. And in terms of regularization and other choices that we make for the network, there is a huge trade-off that needs to be made between regularization and incremental learning. So if you want to learn for the new classes, you would have to perhaps give up on the performance of some of the old classes. And on the contrary, if you want to have a good regularization, we may lose out on the performance of the new classes. And again, another practical thing that was observed is that the standard technique that is used, or dropout, is kind of tends to work better when we are training in an incremental fashion compared to the weight decay technique that is used for learning networks. Okay, so what I'm going to do is okay, maybe just go to this part. Right, so I promised that maybe we're going to look at another type of model instead of classification, but in the interest of time, I'm going to skip to takeaways, but I'm going to make all the slides available on the tutorial website. So, for you to see an example of one work that we did for object detection. So I'll skip straight to some takeaways, and then we can take questions. Right. So, given all these methods, how do we, where do we stand, and what do we look forward to into the future? So, the future desiderata could be that of handling this issue of memory well, where we might want to have a constant memory for our models. For example, if you want to deploy them in embedded devices, the models that you have learned, we might want to have just a constant memory for that, and as soon as you update the model. And we would also like to maybe move away from knowing all the tasks, like the set of tasks that are going to come up, and maybe going sort of task agnostic. And there have been some recent advances on this, and I just put one example here, a method called curl, which doesn't look at what is the task that is there. It kind of does it in an unsupervised, or let's say a self-supervised fashion. So it's an interesting work to follow up, and there are some follow-ups to that particular work as well. And another thing that we might want to consider is not, instead of saying that we don't want to forget any of the previous information that we have, we might want to say that we would like to have some forgetting, but in a graceful fashion, because we, as humans as well, we don't remember everything that we have seen right from our birth. We kind of give preference to maybe some of the more recent stuff, but we may forget something that is very, very dated. And then finally, one of the things that is typically done in the context of incremental learning is to take our standard data sets and to kind of artificially create incremental scenarios where we say that, okay, I have 20 classes, I'm going to split them up into chunks of 2 classes, let's say, and have 10 tasks that I want to learn incrementally. So this isn't naturally an incremental learning setup. We kind of created it. It works fine as an initial test, but as I heard at ICCV, someone famous said that they don't like dataset, and it's more a problem than a solution. And they were encouraging us to go towards a more continuous stream of data. So data keeps coming as a stream. And this is a perfect setup for incremental learning, where you have stream of data coming over time, and we would like to learn from the beginning and go all the way to the end and kind of gracefully forget some of the less important stuff. So with that, I will end this part of the tutorial and just give a pointer to a very nice workshop that happened on the 14th of June on continual learning in computer vision. And many of the talks are available on YouTube as well. So for people who'd like to follow up on what is the latest methods from CVPR, this could be an interesting starting point. So with that, I'll be happy to take any more questions that you find, Spyros.
Okay, yes. So there are some questions about PACnet. So previously,
Okay. Mm-hmm.
So if PACnet, what is the advantage of PACnet over simply having separate smaller networks for each task? And if there is any type of knowledge sharing between the tasks in PACnet?
Right. I don't remember all the details of the method, but the advantage of having one single network with all the tasks is there is a potential for kind of, leveraging information that you have from, other tasks as well. And I think it also depends on how you're pruning. It means that in some ways that the network has already kind of seen all the data, and we're kind of fine-tuning some of the parameters that are there. So I think obviously you can have separate networks, but the disadvantage will be that when you have a test sample, you don't know which of the previous networks you should test with. So it is good to have a single global model where you just pass your test sample through this single model, and you get your output, which can be any of the previous classes. Whereas if you have separate networks, you need to do a pre-step of deciding which of the networks you'd like to test. And this is information that is typically not available at the in the test phase. Okay.
Another question is if this method, PACNet again, I think it refers to, works for stream learning.
Sorry, works for?
For stream learning.
Stream learning. I'm assuming that means data coming in as a stream, or?
I think so, but probably. It's not.
Yeah, I mean, I would guess so, but you would still need to know the total number of tasks, right? So it is not, I guess, strictly speaking, a stream learning method. But yeah, if you know the total number of tasks, you can just to make decide what is the percentage you're going to prune. And maybe I'm here diverging from the original method and the choices that were made in the original work, but I'm kind of interpreting it as a framework. So if you were to decide on how to prune, what is the pruning percentage and for each task, you do need to know the total number of tasks. So you don't run out of space, so to speak, for the final task. Yeah.
And there was another question, which is about distillation. If distillation predicting the labels from the previous time steps, if the intuition that it's preventing catastrophic forgetting is correct.
So distillation can be, is a generic word for just having, computing a difference between what was there previously and what is now the current state of the model. And this can be done at different levels. Could be the prediction level, could be, before the prediction level. So based on that, you can compute the distillation. So that is also a possibility. And there are works that do use this kind of distillation also between the old and the new networks.
And maybe a last question.
Sure.
The question is if there is a Bayesian way of phasing out tasks that are dated.
So there is a whole body of work which I completely ignored, and which is being called as Bayesian continual learning. And there is a lot of work which I haven't covered in this part of the tutorial, and I wouldn't do justice to say anything on that without going into detail. So I would encourage the viewer to see this whole other literature on Bayesian continual learning, and there's a huge bunch of work that has been going on that. Okay, so maybe in the interest of time, we stop here and move on to the second talk. So thank you, everyone, and let's see you around on the second.
Thank you, Karteek, for the presentation, for the wonderful presentation. I will start my presentation in a couple of minutes, in 1 minute. So I will start my presentation now. Andrei, is video all right?
Yes,
okay.
it's visible on YouTube.
Okay, nice. Okay. Hi everyone again. So I'm Spyros, I'm a research scientist at Valeo AI, and now at this part of the tutorial I will present you the few-shot learning methods. So the agenda of this tutorial will include the introduction, where I will explain what is the few-shot learning problem, what is the meta-learning paradigm that many few-shot algorithms follow, and how to evaluate few-shot learning algorithms. Also, I will describe you the main types, the main flavors of few-shot learning algorithms, and what is the few-shot learning without forgetting setting. So let's start. So the image of this picture is called the okapi. It's a relatively uncommon animal in the sense that many of us might not have seen it before. The reason that I'm showing you this picture is not because it's a nice animal, which is this, but because even if you have never seen it before, this image would be probably enough in order to learn to recognize it from now on. And this is thanks to an incredible ability of the human brain that is able to learn new concepts or new visual concepts using very few training examples. In contrast, deep learning methods or machine learning methods require thousands of training examples in order to learn to recognize some concepts. So there is obviously a gap between how humans learn and how machine learning methods work. The goal of few-shot learning is to close this gap. Few-shot learning actually started before the recent deep learning evolution, but in this talk I would only focus on methods based on deep learning. So more formally, what is a few-shot classification? Imagine that you have 5 classes. Each of them represents an animal. And you want to learn those classes in order later on to be able to classify some test query examples. Unfortunately, you have only a single training example for each class, otherwise a single support example per class. So this is a 5-way, one-shot classification task. It's called 5-way because you have 5 classes, and one-shot because you have a single training example per class. So more generally, in few-shot classification, you want to be able to solve n-way k-shot tasks, where n is the number of classes and k the number of training examples. And k can be as small as 1. So the question is if this is possible with the standard deep learning methods, So the truth is that if you try to train from scratch a classification network with such limited amount of data, then you will you will certainly overfit on the training data and you will have poor accuracy on the data. So all few-shot learning methods, in order to overcome this data scarcity and avoid overfitting, they follow a transfer learning recipe. This transfer learning recipe prescribes 2 learning stages. During the first learning stage, in general, you train a model not on the problem that you actually want to solve, so not on the classes that you actually want to learn, but on some other similar problems for which you actually have many training data. The purpose of this stage is to acquire general knowledge about the world, or general knowledge about the type of problems that you want to solve. And then during the second learning stage, you adapt the model by transferring knowledge to the problem that you are actually interested to solve and for which you have limited data. So more specifically, in the context of few-shot classification, during the first learning stage, you train somehow a few-shot model using many training data from some base classes. And then during the second learning stage, you adapt this model to the novel classes, which are the classes that you really want to learn to recognize and for which you have limited training data. So in the few-shot literature offered, the base classes are called the training classes, and the novel classes are called the test classes. And there is no overlap between those 2 sets of classes. And more generally, there is no overlap between the data on the first learning stage and the data on the second learning stage. So a very common transfer learning example for the few shot problem is on the first learning stage to pre-train a typical classification network on the data of the base classes. Then on the second learning stage, you remove the last output layer and replace it with a randomly initialized one that has as many outputs as the novel classes that you want to learn to recognize. And then the other layers are copied as they are. And then you fine-tune everything on the training data of the novel classes. So you optimize the parameters of this network on training data of the novel classes. So this fine-tuning scenario, this pre-trained fine-tuning has worked well in general. But when you have extremely few data on the second learning stage, then, so in the few-shot scenario, then there is high risk of overfitting, even with fine-tuning. So because of that, the goal of few-shot learning algorithms is to devise transfer learning methods that would work well in this extreme scenario, this few-shot scenario. So most, but not all of those few-shot methods use the meta-learning paradigm, the learn-to-learn paradigm. So what is meta-learning? So let's see the few-shot classification as a process. So this process has two types of inputs, the labeled support data and the unlabeled query data, here and here. So given the labeled support data, the learning algorithm, so the stochastic gradient descent, will learn a classification model for using this data that will be used for recognize those classes. Then you will use this model in order to classify the test query examples, and the final output of this process would be the predicted labels for the query images here. So in meta-learning, instead of actually training the classification model, we train the learning algorithm itself. To do that, we need to implement the learning algorithm with a meta-learner model, f of theta. We will not examine now how exactly to implement it, but we will give the general idea. Then, after we implement it with the meta-learner, we optimize it. We optimize the meta-learner on solving few-shot classification tasks. So, in order to do that, you need, first of all, to be able to backpropagate through the entire few-shot classification process. So you need to be able to backpropagate both from this model here, the classification model, and through the meta-learner, in order to be able to compute gradients with respect to theta, which are the parameters of the meta-learner, and thus optimize your meta-learner. So let's see how exactly you train the meta-learner. The key idea is to train it on the same conditions during the first learning stage, to train the meta-learner on the same conditions that would be used during the second learning stage. In meta-learning, usually the first learning stage is called the meta-training, while the second learning stage is called the meta-testing. So to train on the same conditions, you have to train the meta-learner, as I said, on a distribution of training few-shot tasks, also known as training episodes. So to construct, how to construct this distribution using your base class data. Imagine that you have 100 base classes, and you want to learn a meta-learner for solving few-shot tasks that consist of 5 classes with a single training example per class, as this example here. So to construct such training tasks during the first learning stage, you sample first randomly 5 classes from the 100 base classes that you have available. And then for each of those sampled classes, you sampled K support examples and M query examples. In this case, K, so the support examples per class is only 1. And this is how you construct during training a distribution of few-shot tasks with which you train the meta-learner. So the meta-learner, given this distribution, it has to optimize this objective in order to learn its parameters. So in this objective, S and Q is the data of an episode. So specifically, S is the support images, so those over here, and Q are the query images and their labels, so those over here. So in this objective, there is an inner part. This inner part consists of the meta-learner getting as input support data and generating a classification model, M of V. Then this classification model is applied on the query images, and you compute the classification loss. So the outer part is to optimize the parameter theta of the meta-learner so that the classification loss of the produced models is minimized. Maybe it would be easier to understand with this meta-training procedure. So the first step of this meta-training procedure is to sample a training episode of support data and query data. Actually, you can sample more than one training episodes to have a mini batch of episodes, but now we'll restrict it to make explanation to a single episode for simplicity. So on the second step, you use the support data of the episode, you give it to the meta-learner, and it generates a classification model, MOV, which is specific to these classes, to the classes of the few shot tasks that you just sampled. Then you use this classification model in order to make predictions for the queries of the few shot tasks that you just sampled. So you make predict probabilities for those tasks, for those queries. And then on the fourth step, you compute the classification loss over the queries, and you backpropagate over this loss in order to compute gradients over the parameters theta that you want to optimize. So then, having gradients of theta, you can optimize them in order to optimize your meta-learner. So the classification loss can be the typical cross-entropy loss. And this is how you train your meta-learner during the first learning stage, or otherwise during the meta-training time. So then during the second learning stage is the stage where you evaluate your meta-learning, or the testing time of your meta-learning. So during this stage, the meta-learning remains fixed. You don't train it anymore. Specifically during this stage, you will be given a new few-shot classification task, this one, that consists of novel classes. And the meta-learner will get the data of this few-shot task. It will generate a classification model, and then this is the model that we'll use for recognizing from now on these novel classes, the classes of this few-shot task. So if we want to see the parallels between the typical supervised learning and meta-learning, then the training part of supervised learning is the meta-training in meta-learning. So this is the first learning stage. Testing in supervised learning is the meta-testing time of meta-learning. So this is a second learning stage. It happens during the second learning stage. In supervised learning, you have a mini batch of images, and in meta-learning, you have a mini batch of episodes. In supervised learning, you have training data, and in meta-learning, you have meta-training data, which is essentially the distribution of training few-shot tasks with which you train your meta-learner. And in supervised learning, you have test data, and in meta-learning, you have meta-test data. So everything you add meta, actually. And this is the distribution of tasks on which you evaluate your meta-learner. So the test few-shot tasks. So I'm going to point to clarify what is the distinction between few-shot learning in general and meta-learning in general. Few-shot learning is any transfer learning algorithm, any transfer learning method that targets on transferring well with limited data. For example, it can be the simple scenario of pre-training and then fine-tuning, or using, as we'll see later, some metric learning-based methods, or using meta-learning techniques. Meta-learning in general is the idea of learning the learning algorithm, or otherwise to learn the optimization algorithm. And it's ingredient of many few-shot algorithms, but it's actually used on other settings, such as multitask learning or reinforcement learning, and so on. In this talk, I will focus on the few-shot visual learning, or few-shot classification. So how to evaluate the few-shot algorithms? So the evaluation of few-shot algorithms happens during the second learning stage, or otherwise the meta-test time of a meta-learner. So to evaluate a few-shot algorithm, you need to have a held out set of classes that you didn't use for training or the first learning stage. And imagine, for example, that you want to evaluate on solving 5-way one-shot test tasks. So in order to evaluate, you sample a large number of 5-way one-shot tasks from your held out set of classes. You compute the accuracy of your few-shot model on the test query examples, and then finally report the average accuracy on the query examples over all the sampled few-shot tasks. And this is how you evaluate a few-shot algorithm. Common benchmarks for training and testing few-shot algorithms is Omniglot, that consists of more than 1,600 characters from 50 different alphabets. And for each character, which is a class, there are around 20 instances. And there, the common setting is to train and evaluate for 5-way and 20-way classification tasks using a single training example or 5 training examples per class. Another more common dataset is Mini-ImageNet. Mini-ImageNet, as the name suggests, is constructed from the bigger ImageNet dataset, but is reduced in a way for faster experimentation. Specifically, its images are downsized to 84 times 84. Also, instead of 1,000, it uses only 100 classes, of which 64 are used for training. So those 64 are the base classes. 16 are used for validation, so those are the validation novel classes, and 20 are used for testing, so those are the test novel classes. The common settings is to train and evaluate on 5-way, one-shot, a 5-shot setting, so 5 classes with 1 training example or 5 training examples per class. Another benchmark is what I call ImageNet-FC. This contains normal ImageNet size, normal-sized images, and all the 1,000 classes of ImageNet. Among those 1,000 ImageNet classes, it uses around 400 for training, so those are the base classes, 300 for validation, and roughly 300 for testing. A difference between of this benchmark with the previous one is that it trains and evaluates on larger tasks. By larger tasks, I mean that the task consists of more than 300 classes, while the previous one had either 5 or 20 classes. And it uses from 1 till 20 training examples per class. So in general, this benchmark is more realistic and more challenging, and personally prefer it. Also, there are other benchmarks over here, like TRT Mini-ImageNet, one based on CIFAR, and so on. So now we'll describe you what are the main types of few-shot learning algorithms, or what are the main flavors of few-shot learning algorithms. Those are the algorithms that are based on metric learning, algorithms that meta-learn with memory modules, algorithms that are follow the optimization-based meta-learning paradigm, and methods that learn to predict model parameters. As a disclaimer, this categorization is actually loose. Many algorithms combine elements of several types, so it's hard to categorize them to one or the other, and that I'm not planning to do an exhaustive enumeration of all the methods, so just to give you some examples to understand how they work. So let's start with metric learning. So the key idea in metric learning is, during the first learning stage, to train a metric function parameterized with a neural network on the base class data. So what is a metric function? Metric function is essentially a network in this setting that, given as input the images of the base classes, it would learn to map them in a metric space, in a feature space, where if 2 images belong on the same class, then they will have a small distance, as you see here. While if 2 images belong on different classes, so for example, this image here and this image here, so in the class cat and car, they will have a big distance. So having such a metric function, it's easy to distinguish, to discriminate 2 images, to understand if 2 images belong to the same class or not. So after you have trained such a metric function on the first learning stage, then during the second learning stage, you use it as a nearest neighbor classifier in order to classify novel classes. So this stage is actually a non-parametric approach, and because of that, it's simple and works well with limited data. So let's see more what those metric methods do. So this is one of the first methods that use metric learning for one-shot recognition, or maybe the first method. So this is based on the Siamese network, Siamese networks. Siamese networks, given two images, like those two here, it outputs a similarity score. This similarity score, it must be 1 if the images belong on the same class, like in this example, of 0 if they belong to different classes. So in this method, during the first learning stage, they train this Siamese network on the verification task using the base class data. So to verify if two images are of the same class or of different classes. After you train this network on the first learning stage, during the second stage, you keep it fixed, you don't train it anymore, and use it in order to classify the queries of the few-shot task. Specifically, the way you will use the Siamese network is you will compare the query with each of the support examples here, and you will compute the similarity scores, essentially, and classify the query with the label of the most similar support image. So in this case, probably the most similar image. So the image with which you will have the highest similarity score would be this one. And you will classify the query image with the label of this image. So in this case, would be ball. The Siamese networks is one way to implement a metric function, and there is actually quite extensive literature on that. However, here in my talk, I will focus on metric methods that are based on the meta-training principle, the meta-training idea. So the key idea with meta-training is to train the metric model, to train your metric function on exactly the same way that we will use it during the second learning stage. So this was first proposed by this method here. And so what it does, matching networks, is it learns to match images. More specifically, given a few-shot task, so given a query image and some support images of some 4 classes in this example, you first extract features from the query and support images. So this is a feature vector of the query image, and those are the feature vectors of the support images. And then you classify the query image with a differentiable nearest neighbor classifier. Specifically, to do that, you have first to compute the similarities of the query image with each of the support images. To do that, you compute the cosine similarity between the feature vector of the query image and the feature vectors of each of the support images. And this is this part over here. And then you pass those similarities over a softmax operator that essentially constrains them to sum to 1. So after you have computed those similarities, the way to classify the query image, the way to predict, to make a classification probability predictions for the query image is to use this attention mechanism, which essentially copies the one-hot label of the most similar support image. So imagine that if this attention coefficient is 1 with the most similar image, let's say this one, then the classification probability for this image would be the one-hot label of this image here, and this is the output of the classifier. So in machine networks, the meta-learner consists of the feature extractor. So this feature extractor here. And when you generate a model, essentially what you do is you provide the feature extractor and you extract the features from the support images of a few-shot task. So the training procedure, the meta-training procedure for matching networks. So after you extract first a training episode, for example, a training episode, and the second step, you generate a classification model for this task that consists of extracting features from the support images. And then on the third step, you classify the query images using this differentiable nearest neighbor classifier. Then on the third step, you apply the classification loss, specifically the cross-entropy loss, on the query image, and you optimize a parameter set of the feature extractor with respect to this loss. The authors evaluated matching networks on the Omniglot and mini-image dataset, and they saw 2 things. First, that metric learning achieves better results than the scenario that describes view of pre-training and then fine-tuning. And then the second is that meta-training improves over Siamese networks. Siamese networks is essentially the same as matching networks, but without the meta-training procedure. So meta-training seems to be beneficial. Training on the same conditions in this experiment seems to be beneficial. So matching networks, they have some kind of limitation, let's say. If you have more than one training example, more than one support example per class, then you need to match the query with each support example of the class independently. And maybe that's not the best thing that you can do. Maybe there is something smarter. So prototypical networks do learn to extract class prototypes from a class in order to compare images. Specifically, prototypical networks learn prototype vectors that aggregate the information of all support images in a class. So in this case, so for class 2, those are the feature vectors of the support images of this class, and the class prototype would be the average feature vector of those support images, of the feature vectors of those support images. So essentially, the prototype vector is the centroid of the feature vectors that belong to the support set of a class. And in prototypical networks, we extract such a prototype for each class. So you extract the prototype for C2, for class 1, and for class 3 as well. Then, in order to classify the query image, you first extract its feature, which is this circle, this empty circle here, and then you classify to the prototype with the closest distance, with the smallest distance. As distance, the authors use either Euclidean or cosine distance. And more specifically, the probabilities of this classification are computed by passing the negative distances with the prototypes over a softmax operator. So essentially, prototypes are similar to the output weights of a classification network. By output weights, I mean the weight vectors that you have on the last output layer of a classification network, but without bias, by having zero bias. And when you train your meta-learner, so actually when you train your feature extractor, you backpropagate also through the process of creating the prototypes. So more specifically, this is a meta-training procedure for prototypical networks. So after you sample an episode, on the second step, you generate a classification model by computing the prototypes for all of the classes of the sample fuso task. And then on the third step, you classify the queries by computing the distances with the prototypes and passing them over a softmax operator. And then on the fourth step, you optimize the parameters of your feature extractor so that the classification loss over the query images is minimized. The author showed that for more than one training example per class, prototype vectors with Euclidean distance have a better accuracy than individual comparisons with each support example, which is what matching network does. So in this setting, in the case that you have more than one training example per class, it's beneficial, it's better to use prototypical networks instead of matching networks. That's the takeaway. Apart from those two, there are many other methods, many other metric methods based on meta-training. Actually, this is one of the most popular approaches for few-shot learning and few-shot classification. For example, in this method, they implement the distance function of prototypical networks with a relation network, so essentially with a multi-layer neural network. And over here, they use a graph neural network that will get us input the embeddings, the feature vectors of the queries and the support images, and will predict the label of the support image by propagating through the graph neural network information from the labeled support images to the unlabeled query image. Also, some other interesting work is those here that they learn to synthesize additional support examples for the metric function. So additional examples that will help improve the performance of the metric function. There is also much other work. So metric learning based on meta-training is quite effective and in general simple. but it's not that simple in some cases. What I mean by that is meta-training can be bothersome. As I said, meta-training prescribes to train the metric function on the same conditions that you will use it during the second learning stage, so during meta-test time. And this means that you have to train a different metric function for each possible number of classes and for each possible number of training examples per class, which is quite annoying. Also, if the future task for which you want to learn a metric function consists of a small number of classes n, then during training, the majority of the future tasks that you sample, the training future tasks that you sample and with which you train the metric function, would be easy in the sense that the classes that will consist, it would be easy to differentiate, to discriminate between them, and thus the metric function would not have to learn to extract discriminant features in order to solve those classes, those tasks. Because of that, not all methods follow this rule of training on the same conditions. For example, prototypical methods, because of this problem with small n, they actually train during meta-training with a much larger number of classes. But still the problem remains of how to tune all these hyperparameters of meta-learning, the number of classes per task, or the number of training examples per class, or the number of query examples per class. And this problem is common for all the meta-learning methods that we'll see here. But in the case of metric learning, the question is if meta-training is really necessary in order to learn discriminative features, which is what you need. You need to learn with discriminant features in order to use in a nearest neighbor classification way. In this work here, they propose a much simpler way in order to learn discriminative features for metric functions. So specifically, they propose during the first learning stage to train on the base class data, cosine similarity-based classification networks. So what is this? This is a typical classification network, essentially, that consists of a feature extractor that, given an image, it extracts a feature, and a classification head. The classification head consists of the weight vectors for all the base classes, a weight vector for each base class that you have. And in order to compute classification scores for an image, the classification head, the typical classification head, applies a dot product operation between the feature vector that you extracted and its weight vector for each class. So in cosine similarity-based networks, they replace the dot product operation with the cosine similarity or the cosine distance operation. Essentially, this means that the L2 normalize both the weight vector, both the feature vector and the weight vectors of the base classes. So why this is beneficial? What is you should use a cosine similarity-based classifier instead of a typical classifier. So a cosine similarity-based classifier during the first learning stage enforces similar behavior as metric learning methods. By that I mean that training the model to minimize the classification loss, the cross-entropy loss over the data on the base classes, the feature extractor of this model has, given an image, has to learn to extract features that maximize the cosine similarity with the weight vector of the correct class. So imagine that this is an image for the class cat. You extract a feature, and this has to maximize to be close to the weight vector of the class cat, which is this square, black square here. On the other hand, it has to minimize the cosine similarity with the weight vectors of incorrect classes. So for these images here, for these features here that belong to images of the class cat, they have to have a small similarity or high cosine distance with the weight vectors for the classes car and tiger. So the black triangle here and the black circle here. So essentially, this means that the feature extractor will learn to extract features that all of them, if they belong to the same class, would be close to the weight vector of this class, and thus will be close together. And if they belong to different classes, so this case and this case, then they will have big distance because they are mapped close to different weight vectors. And this is something that also metric learning does. And the benefit of this is that learns features, the cosine similarity classifier learns to extract features that reduce the intra-class variance, and thus allows better generalization to novel classes. For example, here I illustrate the TSNE scatter plot for the cosine similarity case and the dot product case. Here we see that the features from novel classes that are learned with the cosine similarity classifier form more compact class-specific clusters that is easier to discriminate between different novel classes. On the other hand, in the dot product case, the features are more scattered around the different classes, so it's harder to discriminate between different classes with the dot product case, with the dot product cosine classifier. So as I say, the first learning stage of the cosine classifier is pretty simple. You essentially train a standard classification network that consists of a feature extractor and a classification weights. There is no meta-training involved here. And then, during the second learning stage, you fix the feature extractor, and you have to learn only the classification weights for the novel classes. Since your cosine classifier acts as similar to metric models, you can actually easily compute these these weight vectors of the novel classes with prototypical feature averaging. So to compute the classification weight of a novel class as the average feature of the support images that belongs to this class. So the same thing that prototypical networks does. So this is quite simple training process in general, and it is shown that with such a simple model, simple to train model, and for which you don't need to train a different model for each one-shot or five-shot case, you can achieve the same or better results than matching and prototypical networks. And especially in this challenging setting of ImageNet, of evaluating on ImageNet, the improvement is more significant. So there is also other words that built on top of cosine classifiers. So you can learn an ensemble of cosine classifiers in order to learn novel classes with few training data, or you can learn dense cosine-based classification models on which you implant new task-specific layers, so new layers specific to the novel classes during the second learning stage, or you can learn to predict class prototypes for the pre-trained cosine classifier, which we will see later, or learn to predict class prototypes by exploiting graph knowledge extracted from word embeddings. I will explain you now the meta-learning with memory modules approach. So in this case, the meta-learner, instead of generating a classification model, it gets an input both the label support data and the unlabeled query data, and directly predicts the labels of the query images. In order to do that, it first stores internally in some memory module, in some kind of memory network, the label support data. And then in order to classify each of the query images, it needs to access this memory and see what is the most relevant information for classifying the query. So you could say that these type of methods treat the few-shot classification as a black box prediction problem. So given those two inputs, what is how to take the correct output here. There is quite interesting work here. I will focus my explanation on this method, the simple neural attentive meta-learner. So the key idea here is to treat the few-shot learning problem or the few-shot classification problem as a sequence labeling task. Specifically, in this case, the meta-learner gets as input a sequence of examples. In this sequence, first come the training or the support examples for which you have already the labels, and then the query examples for which you are missing the labels. And starting from the query images, so starting from the query examples, you classify each of them by accessing by the previous examples, by actually condition on the information that is given from the previous examples. And these previous labeled examples, it can be either the support examples that labels of which are already provided, or query examples that you classified on previous time steps of this sequential process. So you have already predicted a label for them. And the way they implemented this meta-learner, this sequential model, is with temporal convolutions and attention modules. I will not go into details about that. I will just say that the purpose of the temporal convolutions module is to provide for the classification of each query aggregated information about the past examples. And the purpose of the attention module is to pinpoint relevant information on the past examples that are useful for classifying the current query image. So the meta-training routine here is that the few-shot learner, the meta-learner, takes as input, as I said, directly all the support data and the unlabeled query data, and directly makes predictions for the query images, so for the query data. And then you, on the fourth step, you optimize the parameter set of the meta-learner so that they minimize the classification loss over the queries. The advantage of those methods is that they are more generic than metric learning methods, in the sense that they can be applied not only for classification, but also for other type of learning problems, such as regression, reinforcement learning, and so on. However, they have the disadvantage that they are more data hungry. And this refers to the meta-training procedure. So because your meta-learner has more parameters, has a higher complexity, it is easier to overfit on the training task with which you train it, so on the training episodes. Also, another disadvantage is that they are more computationally expensive in order to make predictions for each query, since you have to access the memory in order to find relevant information. I will move now to the optimization-based on methods that are based on optimizing, or optimization-based meta-learning methods. So the key idea here, as was first proposed by Ravi et al., is to treat few-shot learning or few-shot classification as a parameters optimization problem. I will focus here my talk only on the MAML approach, on the model-agnostic meta-learning method. So MAML builds on top of fine-tunings. Specifically, what fine-tuning does is that it starts from some pre-trained parameters, theta, and given the support data S of a few-shot task, it fine-tunes, it trains those parameters, so it optimizes those parameters to respect the training loss on the support data with one or more gradient descent steps. So for the single gradient descent step, you compute new parameters phi with this equation. So those new parameters phi are the parameters of the model for the novel classes. The thing with fine-tuning is that if you have a limited training data during this second learning stage, so there is a risk of overfitting, and therefore you need good pre-trained parameters in order to avoid this risk. So the key idea in the MAML algorithm is to meta-learn the parameter theta, so to meta-learn the initialization theta, so that it transfers well via fine-tuning. So it transfers well using a single gradient descent step specifically, and with very limited training data. And to accomplish this goal, the MAML method optimizes the parameter theta with this objective. So in this objective, there is the inner optimization step here. So in this inner optimization step, you start with the initialization theta, and you apply a single gradient descent step. Alpha here is the step side of this gradient descent step, in order to produce the parameters phi of your model, the model that you use for classifying the classes of this task. So this is the inner optimization step, and this loss is, as you see, over the support data of the task. Then on the outer optimization step, you will use a classification model that you fine-tuned in order to classify the query data of the task. And the auto-optimization consists of minimizing theta, so optimizing theta, so that the classification loss of the fine-tuned models over the query data is minimized. More specifically, let's see the training procedure, the meta-training procedure. So the first step is to sample a training episode. Then the second step is inner optimization step, where you start with the initialization theta. You apply a gradient descent step in order to generate to produce the task-specific parameters phi of the model. Then on the third step, you will use this model in order to classify the queries. And the fourth step, which is the outer optimization step, you optimize the initialization theta so that the loss of the classification model that you fine-tuned on the query data is minimized. So in order to do that, you need to apply a gradient descent step of theta. And in order to compute this gradient descent step on theta, you need to backpropagate through the entire process, which means you need to backpropagate through the inner optimization step here. And so you need, so essentially you need to backpropagate through the gradient descent, and so you need to compute second-order gradients with respect to theta. Of course, this is relatively easy to implement with the automatic differentiation routines of common deep learning libraries like PyTorch and TensorFlow. So this is an illustration that shows in an intuitive way what this MAML objective does. So those phi here are good parameters, good solutions for the few shot training tasks with which you train your MAML algorithm, the MAML model. And then phi theta here is the initialization theta before you start meta training. And you can see that it's, let's say, relatively far from those good solutions for the few shot tasks. So the purpose of meta training is to bring those parameters theta here that are closer to those good solutions for the few shot tasks. And thus, theta is a good initialization in order to fine-tune model for those tasks, using one gradient descent step, for example. So the authors evaluated the MAML algorithm on Omniclot and Mini-Imagent, and they saw that it achieves quite competitive performance compared to the other few shot learning algorithms, or sometimes even better. So the advantages of the MAML algorithm is that it is consistent with the standard fine-tuning procedure. This means that during meta test time, so during the second learning stage, you apply the standard fine-tuning procedure. Also, it's more agnostic. It's actually agnostic to the exact architecture that you want to train, the architecture of the model. And it can be applied to other problems, such as regression, reinforcement learning, so on. The disadvantage of this approach is that you typically require to compute second-order gradients, which might be computationally and memory expensive. And thus, it might be difficult to train large models, large classification models with it. Also, it has this disadvantage of meta-learning that you need to train a different model for each number of classes and maybe each number of shots. And specifically, the constraint with respect to the number of classes is hard in the sense that the meta-parameters, theta that you train, have as many outputs as the number of classes with which you want to train. So they have weights for n outputs on the last layer. And thus, after the meta-training, you cannot easily use it, or you cannot use it in order to solve tasks with higher number of classes. Optimization-based meta-learning is another also very popular method for few-shot learning or few-shot classification. And there is a lot of interesting work here. You can, for example, implement the gradient descent step with an LSTM, which is actually work that precedes MAML, or you can approximate, you can use first-order approximations when meta-learning the parameters theta, and many other things. So there's a lot of work here. One nice method is one nice approach, which is actually hybrid, is related to metric learning, is to meta-learn good features in order to be able to use closed form or convex solvers for learning the weights of the output layer of the network. So to learn good features that when you use, let's say, linear SVM on them, when you learn a linear SVM using the support data of this task, you will learn good weights that will correctly classify the query data of the few-shot task. Or instead of linear SVM, you can use a ridge regression or logistic regression in this method here. I will move now to the final type of few-shot algorithms, those that are called learn to predict model parameters. So the key idea here is to train the meta-learner to predict task-specific model parameters. Because the number of the parameters in a classification model is very big, typically, it's practically possible to predict all of them with a meta-learner. So instead, most of those methods, what they do is they predict a subset of the parameters of a model. Specifically, Pertineto et al., they factorize the weights matrix of the linear lace, the weight matrices of a linear lace, and they predict only the diagonal of this factorization. Or the other thing that you can do is to predict the weights only of the last classification set, of the last output layer. So I will describe you now this later type of methods that predict weights for the classification head. And actually, I will describe you in the context of the few-shot learning without forgetting problem. So what is this few-shot learning without forgetting setting before I describe those methods? So typical few-shot models typically focus on learning novel classes with limited data, and have the disadvantage of forgetting the initial base classes. By forgetting, I mean that their performance is worse than typical classification networks trained on the base classes, or maybe after the adaptation are unable to recognize the base classes. This is an example, this might happen, for example, with MAML. After the adaptation, we will not be able to recognize the base classes on which it was trained. So in contrast, practical applications often require to, after you have trained a model, a classification model on the base classes, to extend this model with novel classes for which you actually have very few training data. And you want to do that quickly without having to retrain on the full dataset, so both the base and the novel class data. So few-shot learning without forgetting targets on this problem and actually combines elements from both the incremental learning and few-shot learning. So now we'll describe you methods that learn to predict the classification weights, and as I said, in the context of few-shot learning without forgetting. So here the concept is that you have already a pre-trained model on the base class data. So this pre-trained model, this pre-trained network consists of the feature extractor and the classification head, which is a cosine similarity-based classification head. And then you extend this model with a meta-learning module, which is this parameter generating function. So the purpose of this module is, given the support data of some novel classes, to produce new weights for those novel classes. So those those new weights of the novel classes will will be used from the classifier, the cosine head classifier, cosine classification head, and in order your now adapted recognition model to be able to recognize both base and novel classes in a unified way. So since your model in its classification has weight vectors for all the classes, both base and novel, it's easy to predict classification scores for all of them, and thus it's easy to have, let's say, unified recognition of both base and novel classes. So in this setting, it's beneficial to use a cosine classification set. And this is because cosine classification head L2 normalizes the weights, the weight vectors of the classes. Thus, all the weight vectors have the same L2 norm. And this is important because otherwise, if you don't L2 normalize, it might happen that the weights that correspond to the base classes and the weights that correspond to the novel classes have different range of magnitude values. So they have different L2 norms. And this might lead biasing, the classifier being biased towards one set of classes. So you have the problem of class imbalance in this case. So with L2 normalization, you avoid this class imbalance problem, and thus it is easier to add the novel weights on the classification head. Also, and thus it's easy to do unified recognition of both types of classes. Also, it can be shown that this conjoint classification head, it can be beneficial on traditional incremental learning settings as well. This is a nice illustration of how the cosine classification head works in the incremental learning setting, on the incremental few-shot learning setting. So the illustration is for the two-dimensional case, when you have two-dimensional features, which are L2 normalized, so they lie in this circle, and two-dimensional wave vectors that will also lie in this circle, since they are L2 normalized. So at the beginning, you have three base classes, so those here, and the weight vectors of those classes are those. So those weight vectors define three regions. So they define decision boundaries. So the features that, the images of which the features lie on this area will be classified on this base class. The features that lie in this area here will be classified in this base class, and the features that lie in this region of the circle will be classified in this base class. So after you add a novel class, a novel weight vector, or the classification head, so you define a new region. And then the features that will be in this region of the circle would be classified in this novel class. So this is how the cosine classification head works in this few-shot incremental learning setting. So the way to train meta-learning modules for this few-shot learning without forgetting setting is quite similar to how you train typical meta-learning few-shot algorithms. There are some distinctions, however. First is that at each iteration, you sample an incremental few-shot episode. So what is this? So in order to create this episode, you sample from the base classes, randomly sample from the base classes, some classes that would act as fake novel classes. And for these fake novel classes, you will sample some support examples, the same way that you will do in the typical few-shot learning set. However, the difference is that for the query examples of this episode, you will sample examples both from the fake novel classes and from the remaining base classes. Then on the second step, your meta-learner will produce a model for classifying both fake novel and base classes. And in this step, you have to ignore the pre-trained classification weights that correspond to the base classes that you sampled as fake novel classes. In fact, what you want is the meta-learner to predict classification weights for these fake novel classes and not use the existing pre-trained weights. So then you use this model in order to classify the queries over both the fake novel and the base classes, and compute the classification loss over the queries, and thus optimize the parameter setup of the meta-learner. So how you can implement this parameter generating function in order to compute classification weights for novel classes. The simplest case is what I already have described, to compute classification weights for the novel classes with prototypical feature averaging. So for each novel class, to compute a weight vector as the average feature vector of the training images that belong to this class. So in this case, you don't need any meta-learning, so it's quite simple. So this solution, of course, might be simple, but it can often or sometimes be suboptimal. And this is because some of the classes in an episode might be semantically or visually similar. For example, here, all white cults, you can say that have similarities. So thus, there are probably correlations between their weights that would be exploited for generating more discriminative weights for the novel classes. And you would like to be able to exploit those weights, those correlations. So one way to exploit those correlations is by generating weights for the novel classes with this attention mechanism. So essentially, in this case, the weight vector of the novel class is computed as a convex combination of the weights of the base classes, or otherwise a weighted average of the weight vectors of the base classes. In this case, the attention coefficients or the convex coefficients of this weighted averaging depend from the similarity of the novel class with the base classes. So, for instance, in this case, if the novel class is the class lion, we would say that the class lion is similar to the class tiger, so they should have a high coefficient. It's kind of similar to the class cat, so you can have a moderate value for this coefficient, and it's not similar at all, so you should have a 0 coefficient for this class. So the way to compute those attention coefficients is to compute them as the average similarity of the support features that belong to this novel class with the classification weights of the base classes. And specifically, this similarity is computed with cosine distance plus the softmax operation. In this work, you can go one step further and learn these interclass correlations with the graph neural network. Specifically, in this case, the graph neural network takes as input initial estimates of the classification weights. So for the base classes, those are the pre-trained weights for the base classes, and for the novel classes are weights that are computed with prototypical feature averaging. And on the output, you want to predict better, more discriminative classification weights for the novel classes. So in this graph neural network, in the graph of this graph neural network, each node is a class, and each edge connects a class with the top most similar classes according to those initial weights. So this graph neural network can take into account those interclass relationships that are encoded by the underlying graph and construct more discriminative classification weights. Also, essentially, this graph neural network implements a denoising contour encoder. By denoising contour encoder, I mean that on the input, during meta-training, you apply Gaussian noise on the initial estimates of the classification weights. The intuition here is that meta-training is such a high-capacity model as a graph neural network, it might be data hungry in the sense that it might overfit on the training episodes on which you train it. So by injecting Gaussian noise during training, you avoid this overfitting. So you regularize the meta-training procedure. So here, all those methods that predict classification weights for a pre-trained classification network are evaluated, and you can see that they have compared to the other methods, they have good performance for the novel classes, and they are also able to recognize both the novel and the base classes in a unified way. Also, the methods that exploit the interclass correlations, such as the attention mechanism and the graph neural network, have better performance than the simple feature averaging. And also, graph neural networks are better in the case of having few training examples, so for the 1, 2, and 5 shot cases. So to complete this type of methods, these type of methods are kind of simple. By kind of simple, I mean that you have an already pre-trained classification network that is trained with a standard supervised method, and you only have to meta-learn module, the parameter generating module for predicting weights for those for this classification network. Also, they are more flexible in the sense that they are able to recognize both base and novel classes, and not only novel. And also during the test time, they have the same speed as typical classification networks. The disadvantage, as I already mentioned, is that the parameter generating module might be data hungry. And the other disadvantage is that since you use a pre-trained network, so you use pre-trained representations, you are constrained by the quality of those representations, which is actually the same happens also with metric learning based methods. This is another interesting work for incremental few-shot learning. I will not cover it because of time constraints. So we'll move to the final notes. So few-shot learning is an interesting and important problem. However, an issue is that the common few-shot benchmarks that most few-shot algorithms use to evaluate are insufficient. What I mean by that is that omnicloud, for example, is saturated. All methods achieve almost 100% accuracy. And on mini-ImageNet with proper tuning, all methods achieve similar results. So it's not easy to distinguish which method is better on this dataset. Also, it's not very realistic since you train and evaluate on small tasks, on tasks that consist of only 5 classes. Actually, there are more realistic benchmarks that you can use if you want to do research on few-shot learning, and I would encourage you to use those benchmarks instead. Another note is that few-shot learning algorithms use meta-learning algorithms and network designs of growing complexity. But it was shown in this work from Sen et al. That well-tuned baselines, such as pre-training cosine classifier, and then fine-tuning only the last layer, can achieve better on performance with state-of-the-art methods. And also these simple baselines can scale better with deeper backbones, with deeper models. So this indicates maybe a different direction for few-shot learning. Maybe instead of focusing on meta-learning schemes, it's better to focus on pre-training richer representations. By richer representations, I mean representations that capture a more diverse set of discriminative factors. So such representations that the idea is that such representations that know more about the world can adapt better to novel classes. So one way to learn such rich representations is by exploiting self-supervision, and this is the subject of the next talk by Relja and Andrei. So this is other subjects that I didn't cover because of time constraints, and you can look it up. And this concludes my talk. I don't know if I hope there is time for questions. Cannot hear something. I cannot hear anything. I don't know if Andrei, are you there?
Yes, I'm here. Can you hear me?
Yes.
So I was replying to some of the questions along the way, but I will maybe you can
nice.
you could provide some richer responses. So we have a question regarding a clarification regarding the fact whether we are using during test time, if we use in the query, if you are using classes that are not present in the support class, in the support set.
For the few-shot setting or for the few-shot without forgetting setting?
I think it was general. It was related to.
In general, if you do few-shot learning, so this is typical few-shot learning, then the examples on the query, the classes for the query examples would be those on the support set only. If you do few-shot learning without forgetting, then the classes on the query example would be either from the novel classes or from the base classes, but not from other type of classes.
Okay. Another question was related to whether the performance of the few-shot learning algorithms degrade if you increase the number of classes, so moving beyond the 5-way.
Yes. I mean, in general, if you have more classes to discriminate, it is a harder problem. So the performance would drop naturally, right?
Yeah.
So it is, yeah.
Okay, and there was another question from Arnab regarding slide 84.
Mm-hmm.
If you can provide some extra clarification regarding the temporal CNN without forgetting setting, but I don't know exactly. Well, Arnab, if you can be a bit more specific.
The 84. This is not without forgetting. So in this case, so the meta learner, as I said, is there some specific question?
So I will ask him if he can be more specific. It will be faster on YouTube.
So in this case, the meta learner takes a sequence of examples as inputs. And since you have a sequence, it's better to use temporal convolutions that at this time step, they provide a context vector that aggregates information from past examples. Mm-hmm. So the receptive field of the temporal convolution would provide information about only the past examples, the previous examples from the current query that you want to classify. So that's the idea of using temporal convolutions.
And there was another question on slide 110. Well, they were asking for more information regarding the diagonalization of factorized weights, of the factorized weights method. Slide 110.
Okay, so if the question, if I can, so maybe it's better to look it up, but what they do there is so it's a weight matrix of a linear layer in a classification network. Either this is a weight of a convolutional layer or for a fully connected layer, is factorized. And there you have some diagonal weights, and on the left and right some normal matrix, not diagonalized weights. So you only predict the diagonal weights, while the other are class agnostic, task agnostic. So they are not adapted on each task, but they are the same for each task. And this is the general concept there.
There was another question before. I'm not sure whether it was clarified or not. So this person, I do not understand how the second backpropagation happened from module M to F when the loss was with respect to data corresponding to module. But I think it was somewhere on the early slides.
Is this for the... Is this for the MAML approach or more?
No, I'm waiting for a response. But before there's another question. The question was, so have there been any experiments where the labels are different between the base and novel classes, but the images are the same? For example, in a dataset like iNaturalist, the base classes are higher level, like plant, animal, insect. And then the novel classes are the fine-grained label like species.
Yes, I think the most settings that I'm aware of, usually you assume that you will not see the same images on the second learning stage, not even the same images with different classes. However, I think, so there is some benchmark based on this iNaturalist dataset. I think it's this one, but I think again there they have a long tail distribution of classes, and they just divide them to many short classes, to base classes and few short classes, which are the classes for which you have few training data. I don't think they have they divide the classes in a hierarchical way. And I don't know if the question about
the other question apparently was clarified later on.
Okay.
So yeah, I told them to come back, but if it's still unclear, but apparently it was clear.
So maybe.
So there's another question that I missed. So can you explain the difference between inductive versus transductive few-shot fine-tuning?
In this case, I think in transductive case, what you do is you exploit also, you fine-tune the model in a way that exploits the unlabeled query images. So in a way, when you fine-tune the model, you assume that you have access a priori to the query examples without their labels. That's the setting there.
So actually, this transductive thing goes beyond, goes several years back. I think it was proposed by Vapnik some years ago, where you assume that, okay, you have some test sets and you have access to it, and you want to use it a bit to better improve your predictions. So you kind of leverage in a non-supervised manner the relationship between your test samples to get some extra knowledge such that you will improve your prediction. So it gets to there, and well, across benchmarks, you have some extra information in the end because you have the access to all the queries. So we've seen that this improves, well, with a few points, the performance of few-shot methods by exploiting this extra information. Well, there was another question that I tried to address, but I don't think I'm not sure that I did a good job. So there was a question, I guess it was for you and Karteek. I'm intrigued on also modeled, how is MAML different from Fisher-Bade regularization referred to by Karteek? Can this method learning classification weights be thought of as a model extension like function extension? Can these methods be used to tackle automate handling of out of distribution samples?
I think in the Fisher, the other case, not the MAML, the household. In the, I think it's called the weight, elastic weight consolidation. This method.
Yeah.
You use the Fisher matrix information in order to see which weights are important, and then you constrain the new weights to be close to the important old weights, the important weights of the previous that you learned from the previous classes. While here, just you start from initialization, from the initial on MAML, you start from the initialized features, and you want to conclude to some good parameters for the novel task. And in order to do that, you meta-learn the initialization theta so that it is placed in a way that is easy to conclude to such it's easy to convert to such good parameters, to such good solutions for the few-shot tasks. Andrei, I cannot hear you if you ask anything.
I have turned off the mic, sorry. There are not other questions for now. There is one. So one is, can you recommend some literature studying rich versus poor features when you mentioned self-supervision methods used to make representation richer? So we will...
So, I mean, leveraging self-supervision is in general the subject of the next talk, but here I have some papers that they exploit self-supervision in order to learn such richer, some more discriminative features. So that's what I mean by richer. So such more discriminative features will adapt better to the novel classes. And if you go to this slide, I have uploaded the slides, and you follow these references, you can see such methods. And then on the next talk, I think Andrei and Relja will compare different self-supervised methods.
Yeah, indeed, we'll see a few techniques and what do you mean by richer features in the next slides.
Maybe we should make a break now and
Yeah.
continue, I guess, in less than 6 minutes with the next talk.
Yeah. Yes.
Okay.
Well, if you can unshare the screen.
Yes, of course.
Okay. So let's see, which screen should I share? So we'll start in about 5 minutes after a short break. Spyros, I don't know if you're still out there, but we can take this question maybe later. If there's any additional to cosine Euclidean metrics to measure distance between images classic features. Or are there any topological based methods of compact class representations? I'm not sure if it's, I mean, from the, maybe if you can clarify if it's in the few-shot learning literature or...
About topological methods, I'm not aware, to be honest. But
I'll go ahead, sorry.
But there is this relation networks, learning to compare with relation networks that actually implements a distance function with a neural network. So instead of using a distance function, existing distance function, it implements it with a neural network, parameterizes this part of the procedure. About topological based methods, I'm not aware, to be honest.
Okay, so it's I don't know what time is it in the US, but it's 0.45. So we will start our last session of today, which would be on self-supervised learning. So just to start my timer. So to remove my face. Okay. So welcome back, everyone, after the break. So this is the last part of our tutorial, which will be on self-supervised learning. And this talk will be in a duo with Relja from DeepMind and myself, Andrei from Value AI. So we have seen already two families of annotation-efficient learning. Here's the last one. We'll go a bit into depth with it. We'll first see the motivation behind this type of method. What does it actually solve? Then Relja will give you a tour of the most popular pretext tasks, what types of self-supervised learning methods out there. And in the second part, we'll go a bit deeper into practical considerations for when using these methods and how to evaluate them and where we can apply them. So a bit on the motivation, I will not go too much into here. We all know that deep learning and supervised learning are really good. It's a really strong and cool combo. There's various heuristics that are developed were developed across the years, good architectures, good optimization strategies, and so forth. It's something unbeatable when the task and the data permit it, of course. So I'll be a bit more precise on this matter. So we have already seen that in the introduction of Spyros that regarding the data acquisition and annotation, there's quite a few challenges, costs, and in general challenges that are not easy to address, especially when you go beyond the ImageNet realm. In addition to this argument, from a representation learning perspective, we have other reasons to look for alternatives to a single task or a simple self-supervised setting. So I'll be more explicit here. I'll take pick on a flaw that we have on ImageNet pre-trained models. So in ImageNet, we have one label per image, and which depicts the dominant object in that image. So let's take this image of a dog, of a collie, and we do a test on it. We take we crop some textures of this fur of the dog and distribute them randomly across the image. Then we feed both of these images to a VGG16 network trained on ImageNet, and surprisingly, we see that actually not only the top predictions are the same, but also on the other decisions, the scores are very similar between the original and the texturized models images. So actually, this means that the type of supervision signal can bias the network differently than we would expect. So because it's just an image level label, practically the network does what we ask for it. It finds the textures that fire the most to recognize this object. Although we expected that implicitly it will learn the representation of the object or the shape, actually this is not happening because the supervision signal is not so complete to guide it towards finding exactly the representation of the dog as we know it as humans. And this finding has been reproduced also and extended in subsequent works, where they show that actually neural networks are trained with for image classification are biased towards textures and not shapes as humans. So humans are more. They did a study over humans, so humans fire more on the outline of the objects rather than the texture itself. So we have here the scores for elephant skin and here for cat. So the ResNet 50 model does a reasonable job here. However, when we mix the two, we see that practically the order it's the same from the elephant texture. Although we have a small outline here of a cat, we see no clue of a cat in the prediction. Certainly, this type of flaw can be fixed by adding extra data augmentation, or by adding different supervision. So, for example, if you want to bias more towards shape, we can annotate the shapes. But again, this comes back to providing more and more annotations, which is of course not feasible, and we are not yet to discover all the flaws of these models. So to improve representation learning, we are looking for features that are not specialized towards solving a particular task. In this case, a supervised task. We want something that some features that can encapsulate richer statistics to various downstream tasks. And then an additional motivation for self-supervision is the progress that was made in NLP, natural language processing, where we have a variety of self-supervised methods. The most known one probably is Word2Vec and now BERT, which are all trained in the self-supervised manner, and they're used systematically across all sorts of tasks as features to them. So I give here an example of a self-supervised self-supervised method on the task on text. So here I take some text from Wikipedia. I have the complete sentence. I remove one of the words, and now I ask my network to, given this sentence, to predict me the missing word. So it's not always the word at the end. It can be also something in the middle. And the classification now, it's posed as a classification problem with each word having its own class. So we have like a few thousand classes where you have to classify from. A similar task in NLP is sentence order prediction. So we have two sentences and we have to predict whether sentence B is the one that is following sentence A. In this case, we can see, well, we have sentence A, the man went to the store, and the second sentence, he bought a gallon of milk. So here the label is next sentence. It's a binary classification here. Well, we have a completely unrelated one, penguins are flightless. And this actually helps the model to learn some useful text representations for other tasks. So given these motivations, okay, let me define what is actually self-supervision, at least according to the coverage that we offer here of the area. So self-supervision is a form of unsupervised learning where the supervision signal is not given by a human label, but is found in the data itself. So there's no human involved in the annotation. Certainly there's a human in developing the algorithm, but not in the annotation itself. And to get there, we usually define a pretext task for which the network is forced to learn what we actually care about in terms of representations, to relate a bit to the question about the rich representations before that. And in general, well, most of the pretest tasks you'll see also in Relja's presentation. For most of them, a part of the data is hidden from the network, and the network has to predict what is missing, as we have seen also in the NLP task. So once we have trained this self-supervised network, we can use its features, or you can use this network to fine-tune it on another task for which you have little data available. So an example of a self-supervised task is a work from Spyros, where we train a network to predict the orientation of an image. So we rotate the image with 4 types of rotations. We feed it to this convnet, and now the problem is a 4-way classification where we have to predict the rotation of the image. And intuitively, this allows the network to learn different features than the ones from upright images, because it has to focus on different cues. The typical pipeline for a self-supervised learning method consists of 2 stages. In the first stage, we train the network on the pretext task, as we have seen in the rotation prediction example. And in the second stage, we removed the rotation prediction head. We don't need it. We are actually caring. We care for this base network and its features. So in this stage, we train a classifier on some other data sets or some other tasks for which we have labels, for example, image classification. Usually this, well, in first approaches, this was fixed and we were using just the features. However, in most of the recent works, the common practice is to use more complex downstream tasks like detection and semantic segmentation and to fine-tune the entire network. In order to better understand what is happening in self-supervised learning, I propose here a metaphor with Karate Kid, which is quite an old film. I was not born when it was launched. So here, in a nutshell, what is happening in this plot, we have this boy Daniel, who wants to learn karate, and he goes to see Mr. Miyagi, who's a karate instructor, and says, "I want to learn karate." Mr. Miyagi, the first thing he does, he tells, "Look, you have to do these tasks, like painting a fence or waxing the car." And well, he puts Daniel do that for several days in a row. So we can see directly the connections. Mr. Miyagi is a deep learning practitioner. Daniel is our ConvNet. The daily chores are the pretext tasks, while learning karate is the downstream task. So after a while, Daniel gets sick of doing these chores, and he says, "Look, I'm not learning any karate." And Mr. Miyagi tells him, "Look, actually, you have learned all the basics of the essential motion patterns and muscle memory, and now you can quickly learn karate." And we see that he's applying these karate movements in place. So here we have a leaked image of Mr. Miyagi during stage 1, where Daniel is working. So the equivalent of a deep learning researcher will be to catching up on papers on arXiv. So now the question is, well, this is a nice idea, but is this actually useful in practice? So, well, if we would have asked maybe 2 years ago, people would have said, okay, it's a nice idea. We don't know yet if it will be useful for something. But as of last year, we see that these methods are increasingly powerful and they're outperforming supervised methods. To be more specific here, to provide some clarifications on this table. So here we have a ResNet 50, which was trained on ImageNet on supervised in a supervised manner. And then we fine tune it on Pascal VOC for object detection and we get these scores. On the lower part, we have self-supervised methods, which are also on ResNet 50, trained from scratch on ImageNet, but without the labels, and then fine-tune on Pascal VOC. And we see that as of this year, we're outperforming this supervised baselines. And this is quite encouraging because it kind of allows us to project ourselves to more complex tasks and to use them to other types of data sets beyond ImageNet. So loosely speaking, there's many types of approaches could fit in this paradigm under the definition that we provide on self-supervision. In particular, input reconstruction, and here I put denoising autoencoders, training with paired signals. For example, when you have some audio and video and an image, and we use one of them to supervise the others, or when you have stereo and you have one view giving supervision to the other. There are some other works hiding the data from the networks, and also some works on instance discrimination that we'll cover a bit later on, where we have an image, you distort it, you mix it with some other images, and you want to recognize the original. When you come with the original, to recognize this distorted image out of this pool of images. So I will define the scope of this tutorial because, as we've seen, there's a large array of methods. So here we will be focusing on self-supervised methods that lead to useful representations and that are obtained through a pretext task and or by hiding a part of the original data to the network. So you'll see in the slides of Relja what we mean exactly by that, and I'll let Relja take the mic.
Hello.
Just stop my sharing.
Yeah, so let me just share my.
Yeah, you can share now.
Presentation. Okay. So I'm Relja Arandjelovic, and I'll give a tour of the various pretext tasks that exist in self-supervised learning. So as you saw in the introduction, kind of a rough gist of self-supervised methods is that you have some input signal, you process it in some way, for example, you distort it or hide parts of the signal, and you come up with a pretext task that you don't actually care about, but you train the network to solve this task, and you hope that useful behavior emerges from it. So one potential example is a classical methods denoising autoencoders. You can think of it as a self-supervised task, where you take an input image, you add some noise, you pass it through an encoder, to reduce the dimensionality. You pass through a decoder, and your task is to actually reconstruct the original image to remove the noise. And you hope that the network learns something about the images, such as that this is digit 2. So I'll give a tour of various different tasks that I classified in the general way they use it. But basically, of course, it's just a very rough classification of tasks. Multiple tasks can fit multiple of these categories, and I can only cover a subset of tasks that exist. And there's often multiple papers that have come up with similar ideas at the same time, and I just can, in the interest of time, I can just present one. And it's not necessarily chronological what I'm presenting here, but I think it follows some logical order. So let's start. So the first type of tasks is, let's say, got to do with inferring structure. So if I ask you this question, so you have these two crops from an image, can you tell me what is their spatial order, or how they're spatially arranged, or these two? So this really gives you the gist of the self-supervised tasks. So basically, you don't need any labels. You just take these two patches from an image, you construct this task. But actually, to solve the task, you need to learn some semantics. So you actually need to recognize that this is a bus, and then you know that this is the spatial arrangement of these patches. Similarly, you need to recognize these are parts of a train, and that the patches are arranged this way. So it naturally means that the network will hopefully learn about object parts and their spatial relations. So the way it proceeds is that you take a patch from an image, you take another patch from one of its 8 neighbors, you pass these two patches through the same neural network, concatenate the features, and then your task is to predict you basically have a cross entropy loss on which of the 8 neighbors you picked. And now, the nice thing, well, one thing is it's kind of, let's say, one of the first self-supervised methods. And it's a very intuitive task. It lets you learn about object parts and their spatial relations. It comes with some negatives as well, like all the tasks, you'll see that there's pros and cons. So for example, it assumes there's some sort of a canonical orientation to your data. So for example, if you have the microscopy images or satellite images, maybe there's no such thing. And also a very common problem with self-supervised methods is that there's some sort of a gap between training and evaluation. So here we're training on patches and we're hoping to learn image representations. Of course, you can apply your network convolutionally and extract features that way, but still you're only training on patches, while at test time you hope to represent whole images. As we'll see later, there's also a bit of a way that the network can cheat. I'll go into this later, but this increases the train evaluation gap. And also, it's not necessarily the case that you need to learn fine-grained representations. So for example, here I don't need to recognize cats versus dogs, because all I need to do is recognize that this is a face of an animal and this is a ear of an animal, and I can recognize the spatial orientation relations. And arguably, there's kind of too few output possibilities. So it's only 8 different spatial locations. Well, we'll see that actually the more you push the task, the harder the task gets, it often means that the performance is going to be better. So the follow-up work uses a very similar idea, but basically they cut the image into patches, but now they kind of make a puzzle out of it. They do a random permutation of this, and the task of the network is to predict the permutation. So it's a very similar motivation to the previous task. You need to learn about object parts and the spatial relations, but the task is significantly harder because there's many more permutations that you need to learn to predict. Then there's a bunch of methods that have something to do with transformation prediction. So you heard about a bit in the introduction, but let's say I give you these images and ask you, how have they been rotated? So to solve this task, hopefully you need to recognize what's in the image. So if you recognize this is a dog, you know that it's been rotated by 270 degrees, and you know that this hasn't been rotated at all because this is a natural view of a frog. Intuitively, you just basically take an image, you rotate it by multiple 90 degrees, pass this through the network, and you just have a classification task to classify which of the 4 rotations were used. And now, nice thing is, again, it's a very simple, well, it's a simpler method. It's very simple to implement, but it's quite effective. Negatives, again, it even more assumes canonical rotations exist, and photographs have been taken in canonical rotations. There's a bit of a train eval gap in the sense that at training time, we see all these rotations, while at evaluation time, we just care about the correctly rotated images. And also a bit of a problem that it doesn't necessarily need to be very fine-grained, because again, don't need to recognize cats from dogs. I need to recognize it's a four-legged animal, and I know how it's been rotated. And there's only 4 different rotations to distinguish between, and I'll show later why it's not trivial to actually do more rotations. And in some cases, it could be the case that this task is too easy. So for example, in the domain, if you're training on street view images, all you need to do is recognize the sky, and you'll know how to rotate the image. So you might not learn good features in those cases. Then there's also another task where you can say, if I give you these 2 images, can you estimate the transformation between them? In this case, a geometric transformation, but it could also be something else. And essentially, hopefully, you need to learn good features in order to solve this task, in order to match them correctly. So the way it works is you take an image, you pick a random transformation, you can extract the features from both variants of the image, and you try to predict the original transformation. Now, this is quite in line with classical computer vision methods, where, for example, SIFT was developed for matching, but later on used very much for classification. But again, there's kind of a bit of a train eval gap. Maybe there's not transformed images at evaluation time. Again, maybe you don't need to be fine-grained enough. Maybe you don't need to recognize cats from dogs to do this alignment. And also, it's a bit questionable how much semantics do you need to solve this task. So maybe you just need to learn good low-level features, types of corners or something, and don't need to actually learn about semantics. And also, features are not necessarily invariant to transformations, because you could learn that 2 different features that tell you how the rotation or transformation has been done. Quite a few methods focus on sort of reconstruction-based tasks. So, for example, as I showed, denoising autoencoders could be considered as one, though it's kind of simple classical method, which, by the way, also gives you a way to denoise your images, which might be a nice side effect. But there's a train evaluation gap, so there's no noise. So training is on noisy data, evaluation is on clean data. And also, it might be a bit too easy, because often you don't actually need to recognize this digit to do this. You just need to look at low-level cues often and do some sort of smoothing of an image or other type of low-level processing. A more challenging task is like this. So if I give you this image with a center cropped out, can you fill in the hole? And essentially, this tells you, well, hopefully, you need to recognize what's in the image in order to know how to fill it in. So this is an elephant, so we fill in the ears and the eyes of an elephant. And this is very much in line with, as Andrei was mentioning, natural language processing, for example, word2vec or BERT, where you mask a word, and all something have tasks. You're supposed to predict all elephants have tasks. So here, to be able to know that I should draw this, I should recognize that it's an elephant, and I should draw a task. So again, you take an input image, you mask it, you do an encoder-decoder type of thing, and you're supposed to recognize the original unmasked image. And you have a reconstruction loss and sometimes also perceptual loss, so this can be a discriminator. And one nice thing about it is that this one probably needs to retain some fine-grained information. So in order to do this task, I need to recognize also what type of elephant it is. Maybe, does it have big ears or small ears? What's its color? But again, there's a bit of a train evaluation gap. So there's no masking at evaluation time. Well, you only train with masked images. Also, reconstruction type of objectives can be too hard, because maybe there's some ambiguity in exactly what color is this shadow, exactly the position of the ear, etc. And maybe too much effort is spent on kind of useless details, potentially useless for your downstream task, such as finding the exact color, finding the exact boundary, instead of just focusing on learning that this is an elephant. Another task is, if I give you a grayscale image, can you tell me the color for every pixel in this image? Again, hopefully you need to recognize what's in the image to do this. So I need to know that this is a fish and what kind of fish it is in order to make these pixels yellow. So again, you take an image, you convert it to grayscale, have some sort of encoder, decoder, and you have a reconstruction loss compared to the original image. And the nice thing is, again, it kind of requires some fine-grained information, and it doesn't need to just recognize this as a fish. You need to recognize what type of a fish it is. But similar to the previous problems, so reconstruction can be hard and ambiguous. Maybe you spend too much time on some useless detail. And also you're forced to evaluate on grayscale images because you've only been training on grayscale images. This last bit is addressed by a follow-up work, where essentially it has two branches. So the first branch is the same as before, where you take a grayscale image and you try to predict the color. But the second branch is you take the color when you remove the amplitude, and you're supposed to predict the amplitude. So now this has similar problems to before, but now you don't need to evaluate on grayscale images because you have both paths. You have feature extractors that take use of all the information. But you're processing different chunks independently, which is not necessarily what you want to do. We usually process all of the input at the same time. Then there's, I think, this CVPR is predicting bag of words from Spyros and Andrei. So there well, reminder of bag of words for newer people in the field. So if you have images, if you have some sort of pre-trained network or classical feature extraction method that extracts features. And what you can do is you can cluster these features across your entire data set and come up with a called vocabulary of visual words, or these kind of clusters that you discover. And this is a visualization of some of the clusters. So for example, so basically you hopefully come up with clusters that correspond to some sort of mid-level to high-level concepts, such as dog's nose. And now you represent your image as a bag of words, meaning that you assign all the features to the visual words, and you have a histogram of how many dog noses are there in the image. And now the self-supervised task proposed here is that you take the image, you compute its bag of words representation, but now you also randomly perturb the image, and now you train another network to predict the bag of words representation. This is a bit inspired by NLP because targets are these discrete concepts that are words, here visual words. Yes, and now the nice things are that representations basically need to be invariant to transformations because you need to reconstruct the original bag of words from a distorted image. And also you need to learn some context reasoning skills because, for example, here you don't see the legs of the elephant, but you need to predict the visual words corresponding to the legs. Negatives are that it requires bootstrapping from this other pre-trained network, and it sometimes can be hard to overcome its flaws. So for example, if this network loses all the fine-grained information, then there's no way to rediscover them because you're just predicting the outputs of this original network. And it has some pitfalls of bag of words. So it's known that bag of words basically lose spatial information because you're just aggregating these words in a bag, orderless way, which is not entirely true because often features have large spatial receptive fields, but it does lose some spatial information. And actually going to spatial bag of words was not improving the results. Now, a very popular bunch of methods uses instance classification as a task. So there, I tell you that this is a crop from an image that it has been distorted. And I give you other crops. Can you tell me which crop from here comes from the same image as this original crop? Now, hopefully, you need to have representations that are robust to various transformations, such as geometry or color, to recognize that this crop comes from the same image as this other crop. So the way it works is you take an input image, you do some random augmentation, and then you classify this augmented image into some of the K pseudo classes, where basically all of the training images are a class on its own. So it's supposed to predict which image it comes from. And now, basically, representations are invariant to the, well, if everything trains well, they're invariant to the desired transformations. And you also need to preserve fine-grained information, because you will have here negatives from other images. You will have other animals, such as, the dog versus cat example. Here you will need to distinguish dogs from cats. The negatives, well, this is kind of the case with all self-supervised methods, but it's very important how you choose your augmentations, because that's what you're exactly training for, to be invariant to them. And all these exemplar-based methods basically might be a bit too fine-grained, because images of the same class are actually negatives. So if I had another image from a different deer, I need to distinguish those two. And furthermore, even if I had the image of the same deer, I need to distinguish those two. So there's nothing that prevents it, for example, from latching onto details in the background in order to distinguish these two images. And also, the original formulation is not scalable, because the number of the pseudo classes equals the training dataset size. So if you had 2 million images to train on, you would need 2 million fully connected layer at the end. But there's ways around this last point, and that is to reformulate it into metric learning. So the way the original formulation works is you take a crop, you classify it, and you say this crop comes from the first image. You take this similar crop, you should classify it coming from the first image, and this other crop comes from the second image. But in kind of a metric learning view, you could extract the features from the image. You have some embedding of the image, and now you're saying the crops from the same image, their embeddings should be similar, while embeddings versus the negatives should be far away. And now this is scalable, because you don't have this requirement of classifying into millions of images. You can use classical losses such as contrastive loss or triplet loss, but recently the info-NC loss has been very popular, so I'll cover it briefly. And this has been used by many methods such as contrastive predictive encoding, MDIM, SimClear, MoCo, etc. So just a slightly more detail into this noise contrastive estimation. So essentially, this is the equation for the loss, but all it says is essentially that loss is minimized if the similarity between the query and the positive embedding is maximized, and if the similarity between query and the negative embeddings is minimized. So it can be seen as a ranking loss. So slightly more detail, you can implement this easily by saying logits are basically all your similarities, so similar query times the positive, query times the negatives, and your labels should be that the first element is positive and the others are negatives. And now essentially, if you do the maths, this is equivalent to just saying cross entropy of softmax of the logits and labels. And now actually, if you squint at it, it's basically like a classification loss that we use for supervised learning. So if you just replace these embeddings for positives and negatives with weights of the positive class and the negative classes, this is exactly the loss that you use to train your supervised methods. So it can be seen as a classification type loss where weights are replaced with the exemplars of the classes. Andrei will go into more details in the next part of the talk. So one method that uses this info-NC loss is contrastive predictive coding, which is kind of a hybrid method between context prediction and exemplar comments. So there you divide the image into many patches, and now the task is to basically predict from every input patch, from every patch of the image, you need to predict other patches in the same image. So it's kind of like context prediction, because you need to reason about object parts in order to predict, if I give you this patch, what is the appearance of this other patch. But it's also kind of like exemplar comments, because you use this NC loss, where you're saying that the prediction should be more similar to the true patch embedding versus the negatives, and the negatives come from the rest of the image or from other images. So it's a very nice idea, because it's very generic. It can be used in basically the same way for images, for video, for audio, for NLP. And it has some pros and cons of the exemplar and context prediction. So it's good that it preserves fine-grained information, because you need to distinguish between cats and dogs because they are negatives to each other. And you need to learn about object parts and their spatial relations. But the negatives are that, again, images of the same class or even the same instance can be negatives. And there's a bit of a gap between training and evaluation because you're training on patches, evaluating on whole images. And again, there's this like context prediction. You're assuming there's some sort of canonical orientations. And training can, in practice, be a bit slow because you have to do to extract all these patches independently. There's a bunch of methods that use videos and exploit the temporal information in videos. So, for example, if I give you this frame from a video, can you ask me what will move? So hopefully you recognize this is a cat, and that's most likely to move and not the bush in the background. So you essentially need to learn to segment objects to solve this task. So the way it works is you take a single frame and you put it through a network. But now the ground truths, you take multiple frames, you extract optical flow, and you threshold it so that it tells you exactly what has moved. But you're supposed to predict this motion from a single frame. So you need to recognize what objects are in order to say, okay, probably this fish is going to move. And now the nice thing is, emerging behavior is object detection and segmentation, and there's no train evaluation gap because you're training on whole images and evaluating on whole images. However, it has some blind spots, for example. So if you have stationary objects, you're not necessarily going to learn about them. Also, it might focus on large salient objects. So here, if there was a small fish in the background, it wouldn't contribute to the loss much, but you would just focus on this big fish. It also depends on this external optical flow algorithm. And it cannot easily be extended to temporal nets. So if you want to train 3D convolutional networks, this task will become trivial because all you need to do is learn optical flow and not learn to recognize objects. Another task is tracking by colorization. So if I give you a color frame and another grayscale frame later, can you colorize this? Well, if you learn to track, this is easy because you can say this thing here is this dress, so it's probably red. So the way it's set up is specifically trying to do tracking. So you're giving it two frames. You're saying, where does this patch come from? And you copy the color of that patch to colorize the image. So it's explicitly telling you should track things. So emerging behavior is tracking, matching, optical flow. You need to maybe segment objects. Negatives are that it might be a bit too low level. Maybe you don't need to learn semantics. You don't need to recognize this is a person. You just need to have good local descriptors to do this matching. And again, well, training has been done on grayscale images, so you need to evaluate on grayscale images. You lose information. So another task is, if I give you a sequence of frames, can you tell me which ones are in correct order? To solve this task is you need to recognize the action and maybe human pose in order to realize that this is the natural way you throw a ball, and this is not the natural way that you throw a ball. So it forces you to recognize human actions and pose. Well, so the way it works is that you pass every frame individually to a network, you concatenate the features, and you have this classifier to say correct order or not. And there are some extensions that go to n frames, and you should pick which is out of place or have a ranking loss formulation for this. And the nice thing is that there's no train evaluation gap. Again, you're training on whole color frames and evaluating on whole frames. And you are probably often learning to recognize human pose, which can be beneficial. Sometimes it's not beneficial, so that's also the cons. Maybe it focuses too much on human pose. And also, it's a bit questionable if you can extend this to temporal networks, because maybe then the task will be too easy because the network might extrapolate the motion, and then it's too easy to say if it's it has been shuffled or not. Another batch of methods use multimodal cues. So, for example, here we have an image, and I ask you, does this sound come with it? I don't know if you'll hear the sound, but let's try. So if you could hear it, you could recognize that it's drums. So probably it doesn't correspond to this image. And that tells you that basically you need to recognize what's happening. You need to recognize that this is a guitar, that the audio has drums, and that these are not in correspondence. So you basically training time, you have videos, and positives come are frame and audio from the same video in the same location, and negatives are audio and frame from different videos. And you basically pass a frame through a vision network, audio through an audio network, and you classify whether they correspond or not. And there has been also an extension that is able to even detect where the object is that's making the sound. And now the nice thing is about these multimodal approaches that they're a natural way of giving you different views of the training data. So you have vision and you have audio. You don't need to crop image, mask parts of the image, make it grayscale. It's a natural two views of the data. And because of this, there's no train evaluation gap. You're training on images, you're evaluating on images. And also you have good representation in both modalities, vision and audio. However, you can have blind spots, so not everything makes a sound, so maybe you don't learn about this. It's exemplar based, so again, videos of the same class can be negative. So if you have two videos of guitars, you need to distinguish between them. And it's a small output space. You just have corresponds or not, but this can be extended to using the NC loss, which gets away from that. In the similar idea is to use narration. So you're saying, does this narration come with the video? And the narration is obtained from speech by automatic speech recognition. To solve this task, you essentially need to recognize what's happening. So you need to say this person is cutting wood. And this narration mentions cutting wood. So they probably correspond. But a problem here is that there's less alignment with respect to the audio case, because the cutting happens here and the person might decide to talk about this later. So it's a similar idea that you pass the video through a video network, you pass the narrations through the narration networks, but you have a multiple instance learning type extension to the NC loss to account for this misalignment, potential misalignments. Again, it has some similar pros and cons. It's a natural views of the training data. There's no train evaluation gap. You get 3 representations in both modalities, but you have blind spots because not everything is narrated about the vision that you see, and it's also exemplar based, so negatives can be from from the same class, and it kind of assumes a single language, not necessarily, but it might be a bit harder to use multiple languages in the narrations. So this was a very brief overview of many pretext tasks that exist. I'll just dump these other ones. Probably it's also probably not an exhaustive list, but there's many works to read about as well. So to the next part of the talk, we'll talk about some practical considerations, Andrei and myself. So in theory, I told you this pretext, you set up a pretext task, you train, and you're done. However, in practice, networks often learn to cheat, to find sort of shortcuts that prevent it from solving the task the way you want it to solve it. I'll give details of this later. So shortcut prevention is essential. And also some details make a big difference, such as augmentation or network architecture. And this really stops being details and becomes essential components of the network. So I'll talk about the shortcut prevention, and then Andrei will talk about the rest. So what is shortcut? So on this example of, if you recall, the context prediction task, where I'm supposed to predict the relative position of these two patches, actually it turns out there's a shortcut. So the network can actually predict for every patch, it can predict its absolute location, which is very surprising because this dog could be shifted to the left easily. So, but the network is able to predict, if I just give it this patch, it's able to predict that it comes from this part of the image. It's not perfect, but it's pretty good. This patch, it predicts it comes from this image. And this is somewhat surprising. So how does it actually do it? Well, it uses chromatic aberration. So brief introduction to that is that basically lenses are not perfect. So different wavelengths have different angles and they get projected differently. So they actually, in this exaggerated example, you see kind of a purple border here, which is not reality, but it happens because of chromatic aberration. So actually, it's possible that the network latches on these cues to see fine details, fine misalignments between the red and green and blue channels. And then if you're able to do this, you can easily solve this task of context prediction without reasoning about semantics at all. So you need to prevent this. So for example, you can just keep one channel and then actually it learns about objects, but this increases the train eval gap. Kind of you're only training on grayscale images or only on red images. Alternatives are also to kind of spatially jitter each channel individually, which might be a bit better. There's other cues as well to solve this kind of task. So for example, if you had strong edges, maybe the network just learns to extend the edges and that tells you what's the relative location of the patches. Or if you just see different border patterns, you know that they match. So you need to take care of this as well. So essentially you take patches that have some gap between them and they're randomly jittered to account for these shortcuts. There's a bunch of others. So for example, if you remember rotation prediction, where you're supposed to predict the rotation of the image. The reason we're only using rotations that are multiples of 90 is that if you used some other rotations, you would need to use a function that rotates an image. And these actually they leave some low-level artifacts that the network can latch on, and it can actually predict the amount of rotation without learning to recognize the object. So actually, these multiples of 90 can be done without special function. They just need flipping and transposing, which leave no artifacts. But it restricts the amount of effort that the network needs to learn because it's just 4 outputs it needs to learn. In videos, there's a bunch of other exploits. For example, the network can learn to do optical flow. So some people do random jittering of every frame individually to prevent optical flow. Or if you have these videos that have these black frames around, actually it turns out that they're not completely black. So if you amplify the values, they're not exactly black because of compression artifacts. So if you had the shuffle and learn setup where you're supposed to predict which frame is out of order, actually these artifacts could tell you which frame is out of order. So you need to remove the black frames. Also, camera motion is not random. So you don't just randomly zoom in and zoom out, for example. It's much more likely that you're zooming in or zooming out. And also kind of the way people take videos is usually you zoom in, this person is playing an instrument and you're zooming into the person. And this can again be a low-level cue that doesn't learn about semantics, but enables you to solve the task. So partial solution is to stabilize the video. There's also some low-level artifacts in audio if you're using the multimodal work. Essentially, there's some compression and sampling artifacts that enable the network to learn if the audio is aligned with the frame or not. So you need to be very careful how you're sampling the audio, or you need to jitter them around. Also, there's a bit of a surprising cheat from batch normalization, especially the exemplar-based methods, where basically there's the assumption of independence is being broken, and because there's positives and negatives in the same batch. And essentially, the batch normalization can peek at other examples in the same batch, so it can kind of communicate across the batch to solve this task more easily without actually learning about semantics. And there's multiple ways to get around that, which are all a bit annoying. One is to just get rid of batch normalization, so you just use layer normalization, but maybe you don't want to do that. One is to make your batches very large, if you have the computational resources for that. Or one is if you're in a distributed setup, you can shuffle the batch statistics around the replicas that prevent you from basically peeking inside your own batch. There's a bunch of other potential shortcuts. For example, this paper has shown that you can recognize the type of camera used to capture an image. So you could imagine that these exemplar-based methods can just recognize what camera has taken an image, and then the negatives are taken by different cameras. And there's some recent work that tries to do, there's been many handcrafted approaches to hunting down shortcuts and disabling them one by one. There's some automatic approaches to that as well. And now I'll leave to Andrei for the rest of the practical considerations.
Yeah. Thank you, Relja. Okay. Just a second. Is this visible? Yeah. Okay. Okay. Thank you so much, Relja. So I'll continue now with the rest of the practical considerations. So Relja has covered the way that the network can cheat. Now we will be speaking about how to improve the performance of the network and to properly implement some of the techniques that we have seen so far. So in the first stage, I will be speaking a bit about noise contrastive estimation, and which is one of the most popular ways of doing self-supervised learning right now. Well, I mean, not popular, the most effective ones in terms of scores on popular benchmarks. So before that, I will introduce some notations. So we consider a set of samples or images X, which have image labels Y from a set of labels. And usually we pass these images through a network f of theta. That is our network generating the embeddings. So in the following, we'll use Q for a query image, for the representation of a query image. So it's the output of f of theta of x. And we consider a separated set of images xy with the corresponding embeddings ki, which can be seen as some keys or representations. So building up on the exemplar classification that we have seen presented by Relja, so studying it a bit deeper, the problem is to recognize a particular instance. So we can formulate this instance. An instance is an image. So we can formulate this instance level classification using softmax. So we can look a bit, as Relja said, squint a bit differently at this softmax. In particular, if you look at the last layer, we can consider each neuron from the last layer as a class level weight vector, Wi. We will put bias with the bias for 0, and this becomes actually a class prototype. So I didn't change much in the softmax logs. Here, WC of K is the index of the W corresponding to the true class of Q, while on the denominator I just do the regular softmax across all the classes. So you can recognize a bit maybe the prototype, some similarities with the prototypical networks that were presented by Spyros. But as we said, we want to recognize instances. So we can do as we've seen in Dosovitsky, where we consider that the entire image, each image is a class in the dataset, so but this amounts to millions of images potentially. Or we can tweak a bit our softmax and make it non-parametric. So this fix consists in replacing the weights, the per class weights Wj, with the image representations k of i, sorry. So now the non-parametric softmax looks a bit like that. I'll put on the side the original softmax. So we see that we have changed the W's with K's. So we are no longer have neurons here. We have embeddings, and we don't iterate over all the classes, set of classes C, but instead we iterate across the samples N. So N here for now is the number of training samples. And among these training samples, we have KQ, which is the instance which corresponds to our query. So either the same class, either the same image with a different augmentation. So this change of parameterization, well, this change of loss is quite nice, because now we focus entirely on feature representation, and we're no longer tied to a specific class representation. So this is this type of approach was proposed by Wu et al. And this is a figure from their work. And now with the non-parametric softmax, we have practically to compare with all the classes with all the images in our dataset. But as we've seen with Relja, well, this N can be very large, can be in the order of millions. There's a few solutions to address this. So the one that is kind of gained in popularity is the noise contrastive estimation, which is an older method from statistics. In here, we cast the multi-class classification into a set of binary classification problems. So in each of these binary classification problems, we have to decide whether the sample that we have is positive or negative. So we have to discriminate between positive data samples and noise data samples. The format of the loss is quite similar, though we have a small difference here. The denominator ZQ is treated as a constant, and we estimated with Monte Carlo approximation. So instead of iterating for each forward across our 1 million data set, so we have to store our 1 million feature vectors and then use them to compute our softmax. What we do, we sample k random j's vectors or ki vectors, and we use that to approximate the denominator. And on this, this turns out to be a bit more effective, significantly more effective than iterating across millions. In the same time, van der Rohe came with the info NCE loss, which is a loss based also on NCE. It's in the context of contrastive predictive coding, where you have seen in Relja's presentation, you see a bunch of pixels, and then you want to predict the next ones to recognize the features of the following pixels, usually in the lower part of the image. So again, you want to discriminate between these pixels and some other negative pixels that are usually sampled from images in the same mini batch. Notice here we got rid of the Monte Carlo approximation because we have fewer well, we can get away with it by sampling patches from the same mini batch. The author showed that there are some connections between to mutual information maximization between the variable q and kq, sorry, and they showed this relation where the mutual information is actually lower bounded by a log of q minus the info NCE loss. So this means that if we minimize this info NCE loss, we're actually maximizing the lower bound of the mutual information. We're making it tighter. And in the same time, this shows that this quantity, meaning the amount of negatives that we compare against, is quite important, and it helps us achieve a better representation. There's another view into noise contrastive estimation that we have seen a bit in Relja's presentation. So it's related to the metric learning perspective of this problem. So in an exact formulation of this loss was identified by Son in Europe's 16 paper, where they extended the triplet loss, where in the triplet loss you have triplets. So we have a query, a positive, and a negative, and at each step you want to pull the positives closer and to repel the negative farther away, which happens here. The problem here is that you do that only one step at a time each time, so you don't learn too much, and it takes quite a while to converge. So what the author proposed here is to use multiple negatives in the same, which are sampled from the same mini batch, and this at the same time with one positive. So here, in a single step, you put the positives closer to each other while repelling many negatives. So this allows you to, with your representation, to cover better your representation space, to dispatch practically the representation such that negatives are farther away and get a more useful representation. So I'm not getting into many details here, but it's just to show you a history of how this problem has been evolved in the metric learning community. So we started with Siamese networks with contrastive losses, where we had just two pairs of two, one positive, well, one query and a positive, or one query and a negative. It has later evolved in triplets, and it has been further developed into multiple negatives, and which is it's a very similar formulation with the info NCE. A key component in metric learning is usually related with hard negatives and hard negative mining. And we have seen that also the negatives are quite important as well in info NCE, although we don't do exactly hard negative mining. We care more about having as many samples as possible. So I mentioned these two views just to bridge them and to have a better understanding on contrastive learning, and to see that how it focuses on the representation learning aspect, and maybe to see if we can import some of the know-how that we have developed across the years into noise contrastive estimation. So now I will cover some tips and some key parts of info NCE implementation, or contrastive learning implementations, to make sure that you are, because there are some delicate parts to tell you how are they're working and where they're important. So the first one is the management of the negative samples. So if you have seen if you look at recent papers on contrastive learning, you would usually see a plot like that, where you plot the accuracy as an amount of, with regard against the number of negatives that we use. So here we reach 8,000. Here in Moco we reach 65,000 negatives, while in Perl we go also in the realm of 64,000. So we can see that all the time the performance is better as we use more negatives. Differently, in another study prior to that, they showed that actually if you have very few smaller sample, very few negatives, so let's say here we have 8 negatives, the performance is actually disastrous. So when we move from 8 to 16 negatives in a mini batch, we can see there's a huge leap in performance from 20 to 60 on CIFAR 10. So okay, we can agree that these negatives are important, and we'll see now some strategies on how to deal with them. So the simplest one, it comes from Siamese and triplet networks, where we use a shared encoder for both queries and keys. So we have the same f of theta, and we update the encoder via all the samples. So do a backprop through all the samples, and this is really nice because all the queries and the keys are consistent. So we learn properly. However, on the downside, well, we kind of limited to the memory on the GPU because we cannot have bigger mini batches bigger than the GPU memory. So we can do as much as the GPU memory allows. This strategy has been extended now in the context of big TPU pods at Google and in large GPU clusters by Chen et al., where they actually managed to get large mini batches ranging from 2,000 to 8,000 samples that ensure plenty of negatives. So here we insert a lot of images in all the encoders. So this encoder is actually distributed across I don't know 60 or 128 GPUs, and we managed to create to have virtually a huge mini batch. And now the loss is computed across all positive pairs in a mini batch. So a trick that is used here to increase the number of samples. Practically, each query can become a key, and each key can become a query. So we compute all the possible combinations of queries and keys in the dataset, and we backfill through them. So on the upside, we have a lot of negatives, which is really good, but on the downside, we have a lot of GPUs to use to come up with. A more memory-friendly approach, which is very efficient from a computational point of view, is to use a memory bank. So in the memory bank, we see we have just a single encoder. Here we pass the query through the encoder, and in order to come up with positive and negative keys, we use a so-called memory bank where we stash all the features from the previous epoch. So now this memory bank contains all the features for all the images in the dataset, and we compare our query with a subset of those, and update our encoder via the query. Every once in a while, we update the memory bank by doing an exponential moving average between our current queue and the KQ in the memory bank, such that it will slowly also update and it will be consistent with my query representation. So on the upside, this approach actually allows us to have very big amounts of negatives while being GPU efficient. However, since we update the memory bank less frequently, we are at the risk of having keys that are older than the queries and incompatible. And finally, we have the momentum encoder from Moco, where we also use a memory bank, but here the update is a bit different. So we don't have a static cache of data, but we have instead a different encoder, f of c, which we call the momentum encoder. So here the momentum encoder produces our keys, but we update it at each iteration. So at each iteration, instead of updating the keys as we did here, we actually update the encoder, and the encoder is actually slowly pursuing the main encoder via exponential moving average. So we have this momentum factor, which mixes our psi with a 1 minus momentum of theta. So we do this at every forward and backward. So here's some PyTorch-like code from the original paper. We have the query encoder and the momentum encoder. We detach the momentum encoder, so there's no gradient flowing through here. we have the gradient passing through f of theta. So we do the backward and then the update, and finally we do the mixing of the parameters. So the nice thing about this is that this is a very elegant method, and it's quite effective in generating large dictionaries. On the downside, we need to tune this momentum. So it works well for these values, which means that the momentum encoder goes really, really slow. While if we go a bit lower than 0.9, the accuracy drops considerably. And another downside of this is that we don't backprop through the memory bank, and we are still at the risk of having this old samples in this queue. So I forgot to mention is that this queue has a fixed size, let's say 65K. And as we add new samples, we remove the oldest ones. So it's continuously updated. Another interesting finding in which makes which improves significantly the effectiveness of contrastive methods is the addition of a small projection head, G of phi here, at the output of our f of theta, of our encoder. So right before the contrastive loss, we have this mapper, non-linear mapper, which is in practice an MLP with one hidden layer and Relja, and that we actually don't use for the downstream task. It's just for the purpose of the contrastive loss. And this really small contribution brings impressive gains. So the gains are somewhere in between 6 and 10%. I had another image here. Sorry, it's missing. I'll have it in the upload. But the interesting part here is that whenever whatever the size of my feature vector, non-linear projection always improves with respect to the no projection at all, and also especially with linear projection, and something really cheap to make. So many people are still wondering where this thing brings such an impressive gain. So in their paper, the authors did an interesting test. Their hypothesis is that G of theta removes the information which is necessary just adds some information which is just specific for the contrastive loss, while leaving intact the features from the main encoder. So they do here a simple experiment where on top of the features from prior to nonlinear projection and after that, they train a simple MLP to predict what was the transformation applied to the image. So if it was rotation, if it was corrupted, or if it's color or grayscale. And we can see that this is quite impressive. We can see that on the normal features prior to the nonlinear mapper, we do well at this task of predicting the rotation, for example, while afterwards it's a disaster. So it's indeed the hypothesis that was launched by the authors, that it helps project the features in a space which is more convenient for the contrastive loss. There's a few words to say on the ingredients that are required for getting contrastive methods getting right. There's a few key ones, which is feature normalization. So we have to normalize the features prior to the softmax. Otherwise, the softmax will tend to go into different values. It can become arbitrarily sharpened by just scaling, and it could be overfitting. Another related solution to that, which is compatible with feature normalization, is to add the temperature scaling, which is this term here, tau, which increases the entropy of the softmax prediction. So it allows, again, not to have very peaky distributions. And we have seen across the experiments that whenever we use L2 norm and this temperature scaling, the results are increasing by a significant margin. So here we get 64 compared to no normalization 57. And another issue related to hyperparameters is that historically, for the second stage, when fine-tuning the network on the downstream task, researchers were using the same hyperparameters from the supervised methods. However, He et al. and Tian have noticed that the features from two networks, same architectures, but trained on the same data, but with different supervision, are quite different. So this means that we should use different specific parameters for self-supervised methods as well. Finally, Another finding from and trend in the self-supervised methods from the last years is that augmentation, which is increasingly aggressive, but also increasingly targeted. So I will be more specific here. The rule of thumb usually was to use whatever works for well for supervised learning, but nobody actually studied does this hold for self-supervised methods as well. And Chen et al. did a huge study on that, on studying many data augmentation strategies, and they evaluated the impact of each one of them individually on the diagonal here, or in combination with in composition with some other tasks. And they noticed that actually the more aggressive you are, the better is the quality of the representation and the better the contrastive learning method behaves. And a good combination of compositions of data augmentations is cropping, random cropping with color jittering and with some Gaussian blur. So in the following, I will move towards evaluating self-supervised methods. So how do we actually evaluate and how do we deal with them to show their effectiveness? So in general, their self-supervised methods, they're evaluated on a large array of data sets and tasks. I invite you to take a look at these papers to see some of these tasks. They will come up with code to evaluate your methods there. And in general, in most benchmarks, the model is pre-trained on ImageNet first, and then on a pretext task, which is usually the contribution of the paper or the method. And subsequently, we fine-tuned it on other data sets of protocols. And now I'll cover 4 major ones. Although there are some fine differences, you might encounter some other ones with some fine differences. So the simplest one is to train a linear classifier on top of our feature extractor, usually a fully connected layer or a linear SVM. We keep our f of theta fixed, and we have a few data sets on which we can perform this, out of which the most popular is ImageNet. So we see here a plot showing the evolution of the scores on ImageNet for self-supervised methods against supervised ones. So here you have methods from 2 years ago. Here you have methods from last year, and this part is methods from roughly from this year. And we see that we're closing the gap towards supervision, towards fully supervised. And this is mostly due to the factors that I was mentioning in the previous slides. There are some critics related to this evaluation on ImageNet because we trained on a self-supervised manner on the training images of ImageNet, and then we fine-tuned in a supervised manner on also on the same training images of ImageNet. So it doesn't reflect accurately the generalization capability of these methods. We can also evaluate on those other datasets that I've mentioned. To test better the generalization of these self-supervised methods, and in general, the ranking doesn't change by much. So you have the same ranking of the methods across the benchmarks. Another way of evaluating self-supervised methods is to look at few-shot learning. So you know now quite a bit of few-shot learning, and we have seen that maybe that there's quite a few similarities in terms of the aims of these two methods, meaning training with as little few annotated examples as possible. So another way of evaluating is to use the same protocol from few-shot learning, where we generate thousands of train stat splits. And once imagine you'd have 2,000 classification tasks, we can evaluate, so we can get some better robust statistics on that. And another way of evaluating these methods is what's so-called efficient classification. Here the problem is similar to linear classification, but we fine-tune the entire network. And differently from linear classification, we take smaller amounts of labeled data. So for example, I can take as little as 1% of the available labeled data and compare against the supervised baseline. So here we usually evaluate on ImageNet, but there's a new dataset which is quite interesting called VTab, which provides many datasets to evaluate on. So they have like 19 datasets where you can evaluate that. So here we compare the accuracy of a supervised baseline. So I trained on ImageNet from scratch, a supervised method on 1%. And here I evaluate, I first pre-train on ImageNet on all the ImageNet images by self-supervision, and then train supervisedly also on those 1% of the data. So, and we can see that consistently we get better results for the self-supervised methods. This means that, here it's a more compelling plot. It means that supervised networks do not generalize well on little data. So here we have CPCV2, where I compare it for 1% of the labeled data. I compare it with CPCV2, and this is the supervised. The red is the supervised. So you can see there's a huge gap in performance. So self-supervised methods actually can do a lot better on this low data regime, while supervised ones are having a hard time. So we can see, well, as we add more data, the gap is getting more narrow. But here in this low data regime, between 1 and 10%, it's a non-negligible gap. So finally, another evaluation, which is the richest one, is transfer learning, where we select a complex task differently from the initial one. So it can be, it can be object detection or semantic segmentation, and we fine tune the entire network there. So this is actually what's more interesting for most of the computer vision researchers, because we can look at object detection, at semantic segmentation, and surface normal estimation and visual navigation. So we have a lot of tasks that we can play on, and can see how well does our method generalize. So this is the same table that I was presenting in the introduction. So you can see that actually maybe you can understand it a bit better now, and what it does. And we can see better the performance, well, the level of performance that was reached now by contrastive methods, well, and some non-contrastive methods with respect to the supervised baseline. I mean, this is really a milestone in self-supervised learning. So there are several ablation studies that study a bit what are the important aspects when using these methods, because there are so many parameters out there, so many complexity of the tasks, so many architectures, pre-training dataset, downstream datasets, and so forth. There's a lot of studies that appeared within this year, and unfortunately I will cover just only a fraction of those, but I will try to synthesize the key ones, and I'll let you discover them. Please go ahead and read these papers, because they're quite interesting. Some of the key findings here is the large impact of CNN architectures. So here is quite interesting. For rotation prediction, for example, if you compare ResNet 50 with RevNet 50, which are very similar networks, on ImageNet, actually, for RevNet 50, you get bigger, well, like almost 10% more points than ResNet 50. So it's important to look also at the architecture. Also, in general, if we increase the size of the pre-training dataset, so in this paper they go up to 1 billion, you can see that the bigger the network, the higher capacity of the network, the better it gets. So in general, ResNet is good, while AlexNet saturates quite fast. When we vary the complexity of the task, of the difficulty of the task, we have some varying benefits. Colorization doesn't benefit too much if we make the problem more complex, but contrastive methods and relative patch and jigsaw are a bit better. There's a caveat on these studies because they consider mostly methods from until the last year. So we don't have yet thorough evaluations on Sinclair or on Moco on these new contrastive works. As we have seen in the previous slides, when we train on low data regimes, we have some significant benefits from self-supervised methods. And another useful finding is that in stage 2, instead of just using the simple linear classifier by freezing the entire net, it's better to fine-tune the entire network. So finally, well, this is an interesting stress test on a data set, on a benchmark of 19 tasks. And we see here that actually, and we compare here against generative methods and semi-supervised ones and training from scratch, which should be here. And we see that in general, self-supervised methods are actually quite well placed. And again, an interesting finding is that whenever you add just a self-supervised head to the initial supervision task, so you have classification, and then you add another head to the network that does, for example, rotation prediction, like here, you always improve the performance. So this is something that you get kind of for free in terms of annotations. I'll go quickly through the applications of self-supervision. So we have seen that self-supervision has been successfully used in several areas. An obvious one is when you want to use them directly. So you train on your pretext task, and then you want to use it with minimal effort to another task. This is the case of these two methods from temporal consistency on video. So at the end of the pre-training, you can use these features directly to align video sequences. So they're really, really powerful features that can use them directly. In this paper by Relja and Andrei on images and in audio, again, for the audio embeddings with minimal effort in terms of training, we train on a very few linear samples with a linear classifier. You get state-of-the-art performances. There's another line of applications, which is kind of similar with what I was saying before, is the ones where you add an extra prediction head, what I was saying before for supervision, where you add an extra head that deals with a self-supervised task, and you keep the main head, which does the classification. So you are in a multitask setting. So here I'll go through a few works that do exactly this. These two head networks. One is the work from Spyros, where the authors were bridging a few shot and self-supervised learning. So they were building up on the similarities between these two approaches, and were using rotation prediction in the first learning stage. And this had a few advantages because we learn richer features, but in the same time they could exploit also non-annotated images, for which they did just the self-supervision task. So this worked quite well in improving the cosine classifier baseline. Exactly the same setting with rotation classification and classification was used by Hendricks et al. And they noticed that this improves significantly the robustness of the model. So here in blue, we have the accuracy against adversarial attacks. And on red, we have normal training without, with adversarial training, sorry. And we can see that rotation prediction brings better features that are more robust to adversarial attacks. And similarly, on CIFAR corrupted, across various data distortions, the blue one, which is auxiliary rotations, is always better. Another application is on domain generalization, where here we want to recognize the same classes across different types of images. So we have photos, clip arts, or paintings. And again, just by doing object classification on the images as they are, and jigsaw classifier on permitted images, leads to improvements in the performance in domain generalizations. So this is just a visualization to show that it enables the network to focus on the objects of interest through self-supervision. So here I have a giraffe. In a normal training, you could see that maybe it was firing on the trees, but actually here it manages to catch up on the animal itself. And the last application will be on rotation for better GAN discriminators. Again, the samples. So we rotate also the fakes and the reals, and we have to predict the rotation. For the real fake classification, however, they use the upright images. And this leads to very interesting results because they reach similar performances under the same condition with they are an unconditional GAN, and they can compare with the conditional GAN. So with less information, they actually get quite significant boosts in terms of in Frechet and Frechet distance and insertion scores, which are typical for GANs. So I'll conclude now with some challenges, open room for future work. So one obvious one is how to improve these contrastive methods, which are very, very expensive. They rely on large mini batches, on complex setups. We have seen in the past few months that there are some works that propose another area direction of research to come back to reconstruction, but not to reconstruction of images of inputs, but reconstructions of features. And there's work from Spyros, and there's a recent work from DeepMind last week that works on the same direction. So we're looking for ways of improving contrastive learning. Another direction is provided by this interesting finding from Hassan et al. In an iClear paper, where they show that training, that we can learn useful features for the first convolutional blocks in the network just by using a single image and trained in a self-supervised manner. So they took an image like that, a high-resolution image. They generate 1 million crops out of it, with different data augmentations. And actually, when training this in a self-supervised manner, the features from the first two residual blocks are of the same quality in terms of linear classifiers with supervised ones and also self-supervised ones trained on the same amount of images. So the question that is put in this paper is how to deal with the other part of the network that is left unsolved, the ones that it's in the upper layers and which is actually well important for classification. And finally, as you might have seen in the evaluations, at least in the pre-training part, most of the works tend to focus on the ImageNet-like data sets where you have just one dominant object per image. Well, there's other cases like in autonomous driving where you have high-resolution images where there's more complex scenes, and the strategies of doing a per-instance recognition of per-image classification is a bit difficult, because if we have an image of a street and then another image of the same street, how do you decide if it's the same one or not? There you might have they might differ by a car or by some pedestrians, which are actually important. And the same thing goes to some areas in medical imaging where the problem is a bit different. Sometimes the image is less structured, and for example, in these cell microscopic images, you don't have any structure. So if you do, I don't know, relative patch, it might not hold too well. Also, if you do patch comparison, you might bump into the problem that Relja mentioned. How do you make sure that you don't have the same patch or not? How do you show that in the negatives you don't have actually some positives? So these are the open challenges that I see for self-supervision, and I would be happy to take any questions if you have. Thank you. So, well, I'll unshare the screen such that also Relja can respond if.
Andrei, you want
Yes.
me to make?
No, I'll open the stream to see actually the questions. I was about to open the stream to see what questions are there. YouTube. Just a second. So, because Relja has responded already to some of them.
Yeah, there is.
So he's quite effective on that.
On the chat.
So I actually don't know what to respond. There were some questions from Victor Scorsia at some point. I don't know if they were responded. Wow, there were a lot of questions in the meantime.
Yeah.
Well,
I think there was a question from Dima.
Yes. Dima,
about why it's a problem. I think my understanding of the question is why there is a problem of self-supervised pre-training on ImageNet and then evaluating linear classifiers using the entire ImageNet.
So it's not that it's. I think, well, I guess many labs are focusing now because ImageNet has always been the holy grail on showing that we're really good. So the problem is that we don't actually see the true capability of these methods. So we train on, we have this 1.2 million images on ImageNet. We train in an unsupervised manner, so we see all those images, and then with a linear classifier, we see them again, and this time we tell them what is the label of those images, right? So we help the network. So if we think about the cheating from Relja, it's us that we are actually giving this extra information to the network, and then of course we get very good, some impressive performance. I'm not just completely criticizing this use because okay, it has some interest because it's still a large-scale image data set, but I think we find better conclusions regarding the generalization of these self-supervised methods in other data sets and in other tasks. So for example, a favorite of mine is object detection, because there is on a different data set, you focus on different parts of the image, and the problem itself is quite different from the initial one, which was usually an image level classification.
Maybe another question. Okay. I think one of the latest questions, I will take it in inverse order, was no. It was retracted, this question, so let's go to the other. It was about if self-supervision helps on domain adaptation, but
on what? On domain adaptation, sorry?
Yes, can you improve I think he meant the unsupervised domain adaptation setting.
Yes, actually, well, there was a paper that didn't make it in my batch. So actually, there's one which is doing some more aggressive. Just to look for my presentation. Okay, some more aggressive domain adaptation, unsupervised. So I think it's one shot domain adaptation. So here it's one shot unsupervised. Is it visible? Okay, so it's one shot unsupervised cross domain detection. It's actually an interesting paper, because what they do, so they do on a per sample domain adaptation. So you want to do object detection. Well, I have a slow connection. I'm sorry. I should close YouTube. Sorry, it's loading. So in this method, so you train your let's say that you train your object detector on Pascal VOC, and then you are on social media and you bump into these types of images which have different styles, right? So there's different bikes and different pedestrians that you don't see on ImageNet on VOC, sorry. So what they propose here is to use to do a per sample domain adaptation. So when you have an incoming sample, you don't know where is it coming from which domain. So what you do, you do some tentative proposals, and on these proposals, you do a self-supervised rotation classifier. So you test different rotations on the boxes, and you do this for a few times. They also use some pseudo labeling, and actually this thing improves the performance quite a bit. And they show some results also when moving from cityscapes to foggy cityscapes. I think just to get down, yeah. So when you move from cityscapes to foggy cityscapes and the other way around, from where? From VOC to clip art and the other way around. So they have a lot of evaluations where they show that this actually is quite effective compared to a simple baseline where you just try to do pseudo labeling or data augmentation of the image.
Okay, there was a question. Now I'm actually randomly sampling questions. Yeah. So there was a question about the MOCO approach.
Yes.
Let me find it again because if momentum encoder has a memory bank, because there is a queue there.
Yeah. Did Relja respond to it, or?
I don't know if I cut it up.
No, so there is some sort of memory bank. Yes, there is a memory bank. In MOCO, they called it a dictionary. I'll go back to the slide. So they called it a dictionary, but it's like an ephemeral bank. So you don't stay in that bank forever like you did in the initial memory bank. So here the memory bank is permanent, so it has a size of n, which is your data set, and you randomly sample from this memory bank. But you always have in this bank all the images. In MOCO, the memory bank is dynamic. It always has the same size, but you always change the keys inside. So it functions like a queue. It works like a queue. And whenever you have a new query, you also have a distorted query that gets a key representation and it's added to the queue, and you remove the oldest one, which is here. So this actually compensates for the fact that you might have older keys in the memory bank, and you always have like a fresh supply of new keys that are compatible for your query. In Moco, they call it a dictionary.
So we'll try to find other questions.
I think one question was, I don't know if you know, I didn't know any works on 3D data and object point clouds and stuff. I don't know if there's something.
In self-supervision or on... I think I saw, but I did well. I think there were some works at this CVPR on self-supervised on polyclouds. I think there was a paper yesterday. I didn't make it for it. On point clouds, no. Well, actually, in these types of approaches in point clouds, there's also some works on radar. You have, which if you remember from the presentation of Relja, you have this multimodal supervision. So sometimes you use these point clouds or the radar to train the other one. So, for example, I've seen an interesting work from the Oxford Robotics lab where they Barnes, I think, where they where they get radar data. No, I don't. Well, I have to look on my other browser. Sorry, I don't have here. So, well, there's yes. So this is it. Learning distraction free radar odometry from pose estimation. So here, well, in radar is a very noisy sensor, and it's difficult to annotate. But they put it on the same car with some LiDAR. And actually, to identify where are the areas where some objects or some obstacles, or where is the area where they don't see, they use the LiDARs as supervision for it. So while it's a particular type of self-supervision, it's multimodal self-supervision. But other than that, I don't know something purely on LiDAR for making use of self-supervision. So I know I am wrong. There was another approach. This is a rather contrastive approach where they do the multiple rotations of the radar image, and they want to recognize the across source.
There was another question: if there is some intuition as to why self-supervision dodges adversarial attacks. So
why does self-supervision dodges adversarial attacks? So it's you can be seen as some sort of data augmentation, right? So well, it was the case for rotation prediction, because you rotate the image, so you cover some of the blind spots that your network has had. So we have seen that another strategy for avoiding for doing better in adversarial attacks is mix-up, where you mix two images. So I think to some extent it amounts to the data augmentation that you insert, but in complement to that is the fact that you are not fooled that easily, because you have because implicitly the self-supervision regularizes the network. So we have seen this a bit in the experiments where we use just 1% of the labels compared to the training from scratch, is that you insert some sort of regularization in your feature by distributing it across your neurons, and you don't fire always on the same patterns or the same textures that allow you to recognize. So I guess this in this way you pad the weight space a bit better across your neurons, and you are a bit more robust to these individual adversarial attacks, where you practically go backward through your neurons, wiggle them a bit to change the class.
I would also say, I think what you and Andrei said in the introduction is that there's one of the arguments is that it's a richer training signal. So you don't just have a single label per image, but you actually construct these tasks which actually make you learn about the world more than just through single labels. And that can also just give you better performance against adversarial attacks, right?
Okay. So are there any hints on how to balance switch easy and hard tasks? That's well, that's not necessarily, well, I don't know if it's only in the realm of self-supervised learning. There was a paper from Dorsch and Zisserman where they were training on multiple self-supervised tasks. And there they managed to find they had a way of balancing them. It was a bit more complex. It was not the usual weighting that you have in the multitask settings in deep learning. So there they had the data-driven task weighting. Maybe really you can know a bit better about that work.
Yeah, so honestly, I don't remember that much, but I wanted to mention that also the evolving losses work, which does kind of a canonical. You have different weights for different losses, but there essentially you have kind of another self-supervised task to evaluate how good is your how good are your weights, and then you're essentially basically they evaluate the features by clustering them, and they're saying that the clusters should obey zip distribution, which is what you often see with like anyway, maybe I'm going into too much detail, but basically there's another unsupervised way of evaluating how good are your features, and then this is the signal to learn to evolve the weights that combine the different pretext tasks. I think in the work you were mentioning, I think it was more like a kind of Adam-like way of, if you had different magnitudes of gradients across different tasks, it would be kind of normalizing for the gradient magnitude per task, if I recall correctly.
Yeah, so well, there are some pointers into multitask learning literature. So you have grad norm, which does quite well. We'll have this uncertainty weighting from Kendall, which managed to give a per task uncertainty. It's not something very specific to self-supervision. So I'll look a bit into the. Okay.
There is a question. If have uncertainty estimates have been used in order to sample hard negatives?
Yes, well, it's not. It's not. Well, in the self-supervised setting, I don't know too much, but in general, hard negative sampling is used in active learning, where you want to select use the uncertainty of your predictions to find the difficult negatives, such that then you will label them and inject them in your pipeline. But in self-supervised settings, I don't recall seeing this.
I don't know if there is any. There is no new question. I don't know if there is an order that we forgot to answer. If there is some unanswered question, maybe you can repeat it, repost it in the chat to see it easier than having to go back. There is I think it was a follow-up question about the adversarial attacks, that how for the model inversion attack, how it can be avoided. Personally, I'm not very familiar with this adversarial attack literature to answer it, but I don't know if the others have to contribute anything. Andrei, you're muted, so we cannot
Sorry,
see your...
sorry. So I guess we know. I was looking that we lost Relja. I'm on 3 screens right now. So we lost Relja. He might have had something because he's working also on things regarding safety and verification of the input. Personally, I'm not very familiar with in general with adversarial attacks and this literature. So I don't know exactly how to respond to this question.
Yeah.
I'm sorry. But really, I responded to quite a few questions. So yeah, well, as Spyros said, if one of your questions was unanswered, please repost it on the chat. It's a bit difficult to parse. Yeah, so the video, there was a question of the video. Yeah, it will be either here staying up, either I will repost it on my account if there will be needing some editing, but we'll anyway, it will be the link will be always on the website. I mean, if there will be a change of URL, it will be on the website, and the same for the slides. They're available up there. Wait, does he says that my slide is incompletely updated? I have to check.
I think this is because there is a gap where the slides of Relja are intervened. That's why maybe he thought that there is some slides.
And well, sometimes it might take for depending on the connection for the image to load.
Because I did a quick check and I didn't see something missing.
Yeah, because well, I pushed what I presented. It was pushed to GitHub, so it was the same. So it shouldn't be a problem. Maybe the images were not loading yet. Okay.
Maybe if there are no new questions, we can finish it. Or yes. I don't know if Karteek wants to add something before the end, or.
You can close it.
Okay.
Okay. Well, thank you, everyone.
Yeah, thank you, everyone, for attending. And
we'll be happy to receive any feedback if you have or questions offline. Well, please do. Also, yeah, if you have some suggestions of improvement and so forth, we'll be happy to receive them.
Yeah, we would be happy to answer them, all the questions, right?
Yeah, also for the questions. Okay.
Bye-bye.
Bye, everyone. I'll disconnect the stream first. Okay, so I ended the stream.